Okay, now we are going to start the chemical bonding in one shot. Okay, so let's start with one by one. Right from the basic, it is applicable from board level to advanced level. Wherever tricks are there, that I am going to tell you. Okay, so let's begin with the very basic definition. What is the definition? Chemical bonding. Okay, what is the chemical bond? Right from that we are going to study, and somewhere I will use the graph. That graph study is also very important. Okay, first of all, what is chemical bonding? Okay, chemical bonding is the forces that holds together, what it will hold together, it will hold the atoms, and what it will form? Molecule. Okay, so are known as chemical forces or valence forces. So the forces that hold together atoms in a molecule are known as chemical forces, are sometimes called as a valence forces, and because of that valence forces only molecules are formed. So that forces which joins together atoms is called as a chemical bond. Okay, that valency forces are also called as chemical forces, or sometimes they are called as a chemical bond. Now, an atom possesses greatest stability when its valence electron shell, that is valency shell also we can say, when valence shell is completely full, that is outer shell is completely full. Normally, we will find the K shell. So K, L, M, N. So this is equal to 1, 2, 3, 4 like that. In the K shell, you will find only 1s. So 1s means only 2 electron it can occupy. So that means that once 2 electrons are occupied, it is stable. So that is called as a duplet configuration. That is called as duplet configuration. Whereas the remaining shells are complete only when they contain 8 electrons. After the K shell, only for this duplet is permitted. Okay, and for rest all, duplet is not permitted. Okay, so for rest all, what is permitted? Then for rest all, octet is permitted. Okay, 8 electrons must be present, then only they are said to be stable. Okay, so let us take the condition where why octet, why 8 electrons only. Simple, octet rule is very simple. Any atom or ion which contains 8 electrons in their valency shell, 8 electrons in their valency shell is stable. Okay. So why it is 8 and why the chemical bond formation takes place, that also we are going to check now. Okay. So before that, let me erase it. Okay, here this is about the chemical bonding and their definition. Now let us see the forces. Okay, chemical bonding reason. Okay, octet rule already understood. It is very simple. Any atom must contain 8 electrons in their valency shell. But why that 8 electron concept, that we will come to know Kossel theory. Okay. First of all, octet rule is understood, but still, where mostly even today also it is followed. But why it is and what is the, still there are some problems with the octet rule. Okay, they are called as a limitations of octet rule. Okay, so limitations of octet rule are, octet rule is quite useful in understanding most of the organic compounds. It applies mainly to the elements of second period. Okay, this mainly it is applicable for what period? Second period only. Okay, and there are three types of exceptions in the chemistry. Wherever you find some exceptions, there only the difficulty will come. Okay, And these are the three exceptions. Octet rule is understood and octet rule is applicable to what it is understood. Now let's see the next part. Okay. Okay, there are three exceptions as I told you. The very first exception, there are in some compound what happens, number of electrons surrounding the central atom. Octet means 8 electron must be there, but still they don't have the 8 electron. Still they are existing. Like lithium chloride is a covalent compound, and here there are only 2 electrons are there. Okay, and beryllium hydride, this is also covalent compound, but there are only 4 electrons are there. BCl3, it is also covalent compound. There are 6 electrons are there. Okay, so they are having less than the octet. That's why the first exception is incomplete octet. Okay. Then second one is in some compounds, the number of electrons surrounding to the central atom is more than the 8. Okay. Like PF5, there will be 10 electrons. Okay. And in SF6, there are 12 electrons. In H2SO4, again 12 electron. IF7, it's 14 electron. Okay, how I am saying, very simple, number of bonds multiplied by 2. Like here, 3 bonds are, each bond is composed of 2 electron, therefore 6 electron. 2 bonds, 4 electron. 1 bond, 2 electron. 5 bonds, 10 electron. 6 bonds, 12 electron. Like that, they are having more than the requirement. This is also called as a expanded octet, or it is also called as a super octet. Okay, when it is less than 8, when it is having 8 electron, there is no problem. One exception is when the electrons are greater than 1. Okay, sorry, greater than 8, then it is called as expanded octet. Okay, sometimes they are having less than the 8, then it is called as a incomplete octet. Less than 8, incomplete octet. More than 8, super octet or expanded octet. Okay, in molecules with the odd number of electron, third exception is odd number of electron. Like nitrogen have 7 electrons, in the valency shell it will have 5, and oxygen will have 6. So this is having total 11 electrons. Okay. Same case with the NO2. Okay. So nitrogen will have 5 electron total. If you take one oxygen also 6. So these are having odd number. So odd number can never be able to form the octet. These are the three exceptions. Incomplete octet. Second one expanded octet. Third one is odd number of electrons. Okay. Okay, till now we understood that chemical bonding. What is chemical bonding? Okay, and we have understood the chemical bonding reason, but to attain octet, but that is not a completely valid because of some limitations. Okay, then the same reason is explained in terms of the energy. Okay, this is also reason of the chemical bond only, but that was in terms of the valence electron. Okay, but still because of the some limitations, now it is explained in terms of the energy. Okay, suppose these are the two hydrogen atoms. Okay, so these are two separate hydrogen atoms. When they approach with each other, when hydrogen atoms approach with each other, then what happens, their energy will keep on decreasing. Okay, then after some time, still if they come closer to each other, see, this is the maximum, this is the distance, I will draw it here. This is the distance comfortable where they have the lowest energy. Okay, so before also they are having the higher energy. If they proceed further, also problem. Okay, So no problem with this much distance, like social distancing. Okay. So like 1.5 feet or 2 feet, like that. This is a comfortable distance. If they're far away, then they are not able to understand with each other what they are saying. If they are too closer, then COVID will be affected. So there will be comfortable distance like that. Two hydrogens, if they are more separated, then also problem. They are too close, then also problem. Because problem in the sense that is energy will be there. Okay. So here this line represents that there is no attraction force between them. Okay. When they cross this line above, then that means repulsive forces are dominating. Okay. When they are below, that means attraction forces are dominating. So the best forces in the universe is attraction forces. So attraction force maximum it will try to get. But beyond this, if they come closer, that attraction is becoming as a repulsion. So wherever this dip is there, maximum dip is there, that energy gap, that energy is called as a, this has some energy, this has some energy. The difference in energy is called as a bond energy. See, attraction is always considered as a negative, repulsion is considered as a positive. So atoms are less stable. Okay, why they are less stable? Because they are energetic. See, this is the energy of atoms. Okay, this is the energy of molecule. Okay, so therefore they form molecule by losing some energy. So for losing some energy, they have to do some work. And what is that work? Formation of bond. So while formation of bond, they will lose some energy. Suppose two hydrogen atoms, this is energetic, this is also energetic. But when they combine and form the molecule, then hydrogen molecule will be there, that energy will be released out. It is going outside. So that means this hydrogen molecule will have less energy than the corresponding hydrogen atom. So this much decrease in energy is there. So whenever energy decreases, stability will increases. Okay. So with this, we can conclude that formation of bond is accompanied by decrease in potential energy. So that decrease in potential energy is also known as chemical bond energy. Okay. So that means whenever there is a bond formation is there. So there was no bond, then energy is more. And when there is a bond formed, then energy is less. Therefore, it is exothermic. It is what? Exothermic. Okay. So this is the explanation of the bond formation. We have two reasons to explain. What are the two reasons? First one is to gain octet according to Kossel-Lewis, and but because of some problems, three problems. What are that problems are called as exceptions. Okay. So because of the exceptions, now it is being explained with the help of the energy also. Okay. So therefore, every atom's aim is to get the noble gas. Okay, noble gas electronic configuration. That is the criteria of the stability. Okay, so for that they are ready to do anything, and that anything will be how many types, and that how you will find out, that I am going to tell you. Okay, so how to get that noble gas configuration, that is fully filled subshells. Atoms of these elements are in a greater stability. Okay, they observed that on observation of all elements, those people are happy who have 8 electrons in their valency shell. So everybody is behind that happiness. Okay, so that happiness is lies with the secret of the happiness is once they get 8 electrons. Okay, so hence do not form compounds. They are happy, so why they will work? Okay, why they will take tension? Therefore, they do not form any compounds, and they are chemically inert. Okay, so if it is a valence electron, whether an atom will form bond or not. Okay, so chemical behavior of entire atom is just decided by its valence electron. How many valence electrons are there? Then whether it will react or not, if react, for what it will react. Okay, so the definite number of valence electrons involved in bonding process. Okay, the chemical association among atoms is achieved by many ways depending on number of valence electron combined atoms. Okay. So how they combine and why they combine, that we are coming to know. But how many types of combinations are there? Three types of combinations are there. Okay. So first of all, what is chemical bonding? Definition only one, and second, reasons for chemical bonding, two reasons. Okay. So here we have the types of bonding. Okay. First of all, there will be ionic bond. There will be which bond? Ionic bond. Okay. So by in during this ionic bond, stability or octet is obtained by the transfer of electron. Okay. Here there is a main keyword is transfer. Their electron will not stay here. So sodium completely transfers its valence electron, and chlorine will completely accepts this electron, takes just electron. Okay. So that it can be 287. Now it is also octet. Okay. Ionic bonding is due to the transfer of electron from an atom with extra electron to an atom with deficient of electron. Then covalent bonding, stability through the mutual sharing. Okay, here nobody is boss. Everybody will share their job. Okay, so here it is mutual sharing. What is that and how we will they will do that we are going to study now. Okay, then coordinate covalent bond, stability through the partial transfer. Okay, or we can say partial sharing. See, I am saying both words. One word I am using from the covalent bond. Okay, one word I am using from the ionic bond. So it is just like a combination of the ionic bond and covalent bond. Okay. So suppose A, okay, A is having three electrons. Okay, or three pens. I will take it as a three pens, red color, blue color, and blue color. Okay, or two red color and one blue color. So it is having extra. Okay, it is having extra. So one red color, one blue color is sufficient. But what it is having extra. Okay, and there is another element B. Another element B, problem with it is having only blue color. That is only blue color pen it is having. Then which type of bond they will undergo? Obviously, see, it is having more than the required. So there will be transfer of electron. Okay. So this electron is transferred to it. Then the bond between them will be ionic bond. Okay. Suppose A is having one electron of the blue. Okay, and B is having one electron of the red. Okay, so now it is also not having both colors, therefore it will share some for some time from the A, and here it will share some time from the B. So now both are complete. So when somebody asks what are the electrons showed to me, then it will show both. And same way when somebody asks what are the electrons in B, then it will also show both. Okay, so that sharing will be done. Understood? Now sometimes what happens, already octet is formed. Okay, already octet is formed, but there are some unused electrons. Okay, then they will donate. Understood? So this donation will be, does not mean that it is completely having authority of that electron. So still A will have some authority, but in the ionic bond it is not like that. Once electron is going to B, now even A cannot say that it is my electron. Okay, because it is lost and gained. But here it is donate and accept. So donate and accept is done intentionally. Okay, with some goodwill, for some goodwill. Okay, so you can write on that your name also. I have donated. Okay, like when you donate something to the charity, then they will write your name also here, that one. Okay, so after, even though somebody is using, your name will be there. So here electron will be used by the B, but still authority is of A. Now during some journey you lost your mobile or money. Okay, now you can't say, even though it is in front of you and but somebody took it, you don't have the proof. So that time it will be ionic bond. Now you don't have authority over that money or mobile. Okay. So that is ionic bond. Understood? So that's why some parts are from taken from the covalent because of the sharing. Some part is taken from the ionic because completely given by one atom only. Okay. So very simple logic. Electropositive when combined with electronegative. Okay. Then it will form the ionic bond. Okay, here this is again
Okay,
an
sir.
explaining through the this example. Electropositive, when electropositive, that means electron extra is there. Electronegative, electrons are less. Okay, so in that condition, what they will do? Okay, in that condition, what they will do? They will donate electron. Sorry, they will lose electron to the needy people. Here, needy people is electron negative. Okay, so once it is completely losing it to the negative atom, therefore it is ionic bond. Here, this is also electronegative. This is also electronegative. Both are having less electron. Okay, EP means electropositive. They have extra electron. What they have extra electron. Okay, electronegative means they have less electron than the required. Okay, so once both are having less, then they will go for the sharing. So once they share, they will form covalent bond. If they share only from one part of the shared electrons are only from one part of the atom, then it will be dative bond or coordinate covalent bond. If both are electropositive, sharing is not required, then electrons will flow like sea. Okay, so that is called as a metallic bonding. So total bonds are four types: ionic bonding, covalent bonding, coordinate covalent bond, and metallic bond. Coordinate covalent bond is also called as dative bond. Okay, so now I think it is clear. So let us take sodium. Okay, let us take sodium, and when it come across with the magnesium, then both are metals, so the bonding between the two metals will be metallic bonding. Okay, and sometimes like NH3. NH3 is very comfortable, but it has some unused electrons. It cannot completely give it to somebody, and it cannot keep it also. In that situation, like small ions like H plus, so then it will ask is to use this. Okay, not it is not giving completely. It will also use, and in the free time that lone pair will be used by the H plus. So then it will be coordinate covalent bond. Okay. So but here in NH3 these electrons are shared. So three electron in NH3, three electrons are shared, two electrons are donated. So donated will cause coordinate covalent bond, and shared electrons will cause ion covalent bond. Okay, but when this magnesium come across with the oxygen, when sodium and magnesium are there, nobody is required electron. But when it goes to the oxygen, oxygen got only 6 electron. It is in the need of the two more electron, and it is having the 2 electron extra. So that extra electron when it transfers, okay, transfer. So transfer means ionic bond. Okay. Sharing means it can be covalent or coordinate. Okay. If both shared electrons are given by one only, then it is coordinate. If one is given by each of atom, then it is called as a covalent bond. Okay. So these are the four types of bond along with their explanation. Okay. Now let's see the next one. So as I told you in the starting only, I will tell you the reason only why 8 electrons. Okay. So that was told by the Kossel-Lewis. Kossel-Lewis electronic theory of chemical bonding. Okay. So this Lewis pictured the atom in terms of okay, first of all, positively charged kernel. Okay, that is nucleus plus inner electron. Suppose if we take the sodium. Okay, so sodium 281, up to this it is kernel. Okay, so this kernel involves 12 protons, 13 neutron, and 10 electrons. So obviously, sorry, it is 11 protons. Okay. 11 protons, right? Okay, 11 proton and 12 neutrons. 23 is the mass number, so 12 neutrons. Okay, so 11 protons and 12 neutrons plus these 2 and 8 electron. This is what we called as a kernel. Kernel is a combination of neutron, proton and electrons other than the outermost. Okay, then the outer shell could accommodate maximum of 8 electron. Okay, why 8 electron? Because he further assumed that these electron occupy corners of a cube. Okay, so that time it was not, atom is not considered as a sphere. It was considered as a cube. Okay, he thought that this is the nucleus with inner core of the electron. Okay, now this inner core of inner core of atom. Okay, so this will consist how many things? Total three things. It will consist. First one is it will contain the neutron. Okay, it will contain the proton. It will contain the electron other than the valence shell. But these corners, how many corners will be there in a cube? 8 corners. Okay, so these corners were occupied by inert gases. He felt that time. That's why inert gases are more stable. Okay, why 8? Then they asked. Then he told because cube got 8 corners, therefore 8 electrons are stable. Okay, so, but afterwards, when structures are revealed, then they said it is not cube. Okay. So, when all 8 corners of a cube are occupied, then they have stable electronic configuration. Okay. So, the clearly shows noble gases which have 8 outermost electron are stable. Okay. And while other atoms are unstable. Okay. Okay, Kossel took only to prove that 8. What is the logic behind the 8? Okay, so but afterwards it is not successful. Nowadays we are not using that. Okay, okay, Kossel-Lewis structure was able to explain maximum things, but only thing he was not successful because of the cube logic. Otherwise, still today also we are going for the Lewis dot structure. Okay, so that we will study once all type of bond, once there is uh, introduction given to all type of bonds, then we will study the Lewis dot structure. Okay, so now what are the types of bond? I told you covalent bond, ionic bond, ionic bond is also called as electrovalent bond, and coordinate covalent bond and metallic bond. Okay, so the majority of the bonds are either covalent or ionic. Okay, and in this chapter most of the topic related to covalent bond only. Okay, so but still we have introduction about the all bonds. Okay, now I think it is clear idea about what will be the coordinate condition, what will be the ionic condition, what will be the coordinate condition, what will be the metallic condition. Suppose copper and zinc, blindly you should be able to say it is metallic bond. Okay, but when zinc comes into the reaction with nitrogen, nitrogen is a non-metal, it is a metal. So non-metal metal ionic bond, and nitrogen when comes in contact with hydrogen, non-metal non-metal covalent bond. After formation of the compound also lone pair is there, then it will form the coordinate covalent bond. Okay, so this is introduction to all, and but we will in-depth study about the covalent bond. So covalent bond was proposed by the G and Lewis again. The bond formed between two atoms. The bond formed between two atoms by the mutual sharing. Okay, mutual sharing of their valence electron is known as covalent bond. And only unpaired electron present in the atom involve covalent bonds. The number of covalent bonds in which an atom involves equal number of unpaired electrons present in it. Okay, so suppose oxygen, oxygen. Okay, then they will have the two electron requirement. So then these are the electron required by the other oxygen also. Okay, the requirement of the same atom will be projected on the both atoms. Okay, so then what it will do, it will share two electron from here, and it will share two electron from here. Okay, so the number of covalent bonds in which an atom involves is equal to the number of unpaired electrons present in it. So why I am only taking these two? Why not I am not taking them? Because only these two electrons are unpaired. Only unpaired electrons are authorized to form bond. Already paired electrons are not supposed to. For example, oxygen, I will write it in the electronic configuration 1s2, 2s2 and 2p4. So here so many electrons are there, but why I am taking only two electron? Just because there are only two electron unpaired. Okay, so like let us take these. Only these two electrons are unpaired. Therefore, oxygen and oxygen will form double bond. Same way, if you take nitrogen, 1s2, 2s2, 2p3. So number of valence electrons are how many here? 3. So 3 valence electrons are there. Therefore, 3 bonds there will be forming. Okay. So number of unpaired is equal to number of bonds. That is what the covalent bond theory. Okay. So let us see further. Okay, like phosphorus atom have three unpaired. I have taken the example of nitrogen. Here, example is of the phosphorus. So in the ground state, so it can form only three covalent bond. That is also ground state. Okay. So what is ground state? See, it will be 3s2, 3p3. So S subshell 2 electron, P subshell 3 electron. Without doing anything, it is having 3 unpaired. But if we wanted to do something extra, then it will ask this electron to move here. That is called as a excited state. So when this electron goes into excited state, then 5 unpaired will be there. So 5 unpaired means 5 covalent bond. Okay. So phosphorus can form two either three bonds or five bond. Three bonds in which state? Ground state. And five bond in which state? Excited state. Okay. Same way chlorine also. So chlorine have 2, 8, 7. So it will form one unpaired electron will be there out of 7. So one bond. Okay. One bond in which state? Ground state. And how many bonds? All 7 electron can be used, okay, with oxygen. That time there will be 7 bonds, okay, but 7 bonds for that electron must be migrated from the 3s and 3p to 3d. Okay, that time it is possible. Therefore 7 bonds, for that it should go for the excited state. It should go for which state? Excited state. Then only it can form the 7 bonds. Likewise, everything you can say. Okay. So let us take sulfur 286. Okay. Now, if it is in the ground state, how many bond? Excited state, how many bonds it can form? Okay. Question is how many bonds it can form in the excited state. Okay. Like in sulfur, electronic configuration, valency configuration is 6. So it will be 3s and 3p. Okay. So better use the whiteboard, I think. Okay. So sulfur atomic number is 16. So it will be 3s2. In the valency shell, it will be 3s2, 3p4. So 6 electrons are there. So now it is 3s2 and 3p4. 4 electrons are there. So once 4 electrons means 2 unpaired. Okay. So now it can use a 3D. So it will use excited state. Excited state means bringing the electron to higher energy level. Bringing the electron to higher energy level. So now it is called as a ground state. In ground state, how many unpaired electrons are there? 2 unpaired electrons are there. Therefore, ground state electronic number of bonds it can form are 2. Okay. But if required, it got the facility 3s2, 3p, this electron also gone, 3p3. Now two electrons are received. One electron received from the 3s, one electron received from the 3p. Therefore, it will be 3d2. Okay. Now, how many unpaired electrons are there? Simple number of unpaired, number of bonds. Okay. So here, when this two electron comes over here, it got the space. It can use the out 2 out of the 5. Okay. So this is the actual configuration. Okay. In sulfur when it goes for the 6 bonds. Okay. So this is what we are going to study in the hybridization also. Okay. So now I think it is clear. Sulfur in the ground state, it will be forming 2 bonds. In the ground state, how many bonds? 2 bonds. In excited state, how many bonds? 6 bonds. In excited state, 6 bonds. Okay. Okay, now types of chemical covalent bond. We are studying chemical bond in that first type covalent bond. So types of chemical covalent bonds, that is covalent bonds also you can say. There are three types, are mainly two types. Okay. So first one is a pure covalent bond. Okay. Second one is called as a polar covalent bond. And actually third one is a combination of these two only. Okay. Pure and polar covalent bond. Okay. So you can take it as a other part also. You can take it as a same part also. Pure covalent bond means the electronegativity of the both bonded atom must be same. Like both hydrogens are there, so equal sharing will be there. Both nitrogen, 4 sulfur, sorry, phosphorus, 8 sulfur, all atom taking part in the bond formation are made up of same atoms, same type of element. Therefore, they are called as a pure covalent. But when it is formed by, okay, so this is electron pair between two dissimilar atoms, then it is called as a polar covalent. Like HF is a polar covalent, HCl polar covalent, okay, and H2O polar covalent. But in some cases like N2H4, so I will draw the structure here. N2H4 will be structure will be like this, N and N, and there will be two hydrogens. Okay, now you have to mark how many polar covalent bonds are there, how many pure covalent bonds are there. This is a mixture of the both. Okay. Okay, very simple. The bond between the two nitrogen, both are same electronegative, therefore it will be pure covalent bond. But between the nitrogen and hydrogen, they are two different electronegative. Here more electronegative, here less electronegative. That will okay. These are the four factors for covalent bond. Covalent bonding is basically sharing. Basically what? Sharing of electrons. So for sharing of electrons, small size of cation. Okay. So that it cannot lose, because if it is large cation, then automatically it will try to lose and form ionic bond. And large size of anion, just opposite requirement of the ionic bond. Okay, for ionic bond it has to lose and gain. So once it is large size anion, it will not gain. Okay, so there are no chances of gaining. Okay, so and cation being small in size, it cannot lose. So next to largest charge on the cation and anion. Already charge is more than this, we will study in the Fajans rule. Okay, in detail what is the effect of charge, that we will study in which rule? Fajans rule. Okay, so Fajans rule is very important. Many type of orders will be coming. Okay, so chemical bonding plays a vital role for complete understanding of the inorganic. Inorganic is depends on how you are strong in periodic table, how you are strong in chemical bonding, and how you are strong in redox reaction. Okay, So if these three chapters you are perfect, then entire inorganic is going to be smooth and fine. Okay. So try to spend more time in the chemical bonding, periodic table and redox reaction so that the entire journey of the inorganic will be easy. Okay. So third, ionization enthalpy. There is, if there is no chance of losing or gaining, then they automatically the other option is covalent bond. Okay. So the tendency of atoms having high ionization enthalpy do not have tendency to lose form cation. Therefore, they automatically prefer the covalent bond. For example, chlorine more ionization energy. And compare electronegativity. Suppose A and B, they are sharing. So there should be of mutual understanding. So one, it should not be happen that one is too kind, another is more cruel. Then sharing will not be proper. Both should be equally cruel or equally kind. Okay. So electronegativity because they are going to sharing. So sharing should be between the equal electronegativities. Okay. These are the factors favorable for covalent bond formation. Okay. Now let's see the next. What are the properties? What are the properties of the covalent bond? Okay. So first, covalent compounds are substance which exist. It can exist in solid, it can exist in liquid, and it can exist in gases. Normally, ionic substances will be in solid state only, but covalent compound due to different wide range of the bond energy. Bond energy is sometimes more, sometimes less. Therefore, due to high range of the bond energy, suppose iodine is a pure covalent compound, but still it is in the solid state. Bromine, it is pure covalent compound, it is in the liquid state, and chlorine, it is also pure liquid substance. Okay. So, but sorry, pure covalent substance, but still it exists in gaseous. That shows that covalent compound can exist in all the three state. Okay. But it is not possible for the ionic substance. Okay. Then covalent substances have comparatively low melting and boiling point, except if they have the 3D solid network like diamond. In diamond, each carbon is connected to how many carbon atoms? Four carbon atoms. So to convert into vapor state and we have to break this strong 3D network. Same is the silicon carbide. It is commercially called as a carborundum. Silica, boron, nitride, these are the 3D network. If they have 3D network, obviously they require more melting and boiling. Okay. Then covalent substance dissolve in non-polar solvents. Okay. They are non-polar, so they prefer to be in non-polar. And solubility of polar covalent substances in a solvent having high dielectric constant and less in a solvent having less dielectric constant. Okay. So this covalent substance dissolve in non-polar is due to pure covalent bond. Okay. In the pure covalent bond, you don't find any type of positive or negative charge. But in case of the non-polar covalents, non-polar solvents, okay, then solubility will be more in the pure, non-polar solvent, pure covalent, and polar covalent bonds are there. Then they are having solubility in the high dielectric constant. Okay, like HCl. HCl is soluble in water because water got the high dielectric constant. But Cl2H2 non-polar, they will be or they are pure covalent. Therefore, they will be soluble in non-polar solvent like benzene, okay, and kerosene, carbon tetrachloride, carbon disulfide. Okay. So what is dielectric constant? Every time we say it is more dielectric constant, actually it is a measure of capacity to break the bonds of the solute molecule. Okay. Solute molecule into ions. Suppose if I am saying HCl, okay, HCl, as soon as it enters into water molecule, and so many water molecule will be around the hydrogen, okay, pulling it outside and makes it as a H plus. and there will be so many water molecule will be around the Cl minus also. So that will be coming out as a Cl minus. This will be coming out as a ion H plus. So this polar molecule is now converted into ions. So the tendency of the solvent, how it can do, how much capacity it got the conversion of polar covalent molecule into ion. That is called as a dielectric constant. That is called as what? Dielectric constant. Okay. So next, after dielectric constant, more dielectric constant, obviously more will be the solubility, more number of solute with polar covalent bond will be dissolved. Okay. So this is what the dielectric constant is. Okay. So polar solvents have high dielectric constants, like water is a polar solvent. Okay. So polar means there will be partial negative sign here, there will be partial positive sign here. Okay. The non-polar solvent have low dielectric constant. Okay. So water is a polar solvent, ammonia is a polar solvent, HF is a polar solvent, CH3OH polar solvent, C2H5OH polar solvent. Okay. And low for the benzene, carbon disulfide, carbon tetrachloride. Okay. So covalent substances are not electrical conductor because for conducting the electricity they must have some charge. Okay. So they have partial charges. Okay, they have what? Partial charges. Okay, polar solvents have dielectric constant. Examples are uh, water and methyl alcohol. Okay. Okay, so here I said as a polar covalent compounds are less are bad conductors of electricity. Okay, the why it is due to absence of any free electrons or absence of any free ions. But exception, actually exception why this is a special case you can say. Graphite contains delocalized electrons. Out of 4 electrons of the graphite, only 3 electrons are participating properly in the bond. 1 electron is not at all participating. That electron can cause the conductivity. Okay. So how it is we discussed in the 14th group, carbon family. Okay. Then covalent compound exhibits space isomerism. Okay. Because covalent bond is directional bond. So space isomerism in organic we call it as a stereoisomerism. Okay. So that is more promptly more occurs in the ionic organic substance, therefore it is discussed. Okay, but same thing can be applied for the inorganic also. Space isomerism, stereoisomerism, both are same. Okay. See, HCl, HBr, HI, HNO3, H2SO4 are polar covalent bonds. Okay. So they are good conductors of electricity because they contain free ions. For conduction, first exception is graphite because they have free electrons. Okay. And these are free good conductors because they have free ions. Okay. It is for them those who are not able to provide neither electron nor ions. Okay. So covalent reactions are slow because they involve breaking bonds. Like when I say NaCl to react, immediately they will react because they are already in the form of the ions. But if I ask HCl to react, first of all, this HCl should convert as itself as a H plus and Cl minus. So that will take as a time. Okay. Just like we can say covalent compounds are like ladies. So they take time to get ready for any work or any job. Okay. And ionic compounds are just like gents. Just they will pick up a shirt and pant, then immediately they are ready for any job. Okay. So because they have lot of adjustments, like hydrogen have to become H plus, Cl have to become Cl minus. By the time it will take, so sodium is already ready. Every time it is with positive charge. Every time it is with negative charge. So covalent compounds are reactions are very slow. Okay. So how you will prove that they are very slow or they don't react? See, Carbon tetrachloride, for the namesake, it have 4 electron, 4 chlorine. And AgNO3 asks only 1 chlorine and it takes a lot of time. Okay. But if you ask you AgNO3 to react with NaCl, fraction of second, you will get white precipitate of AgCl. Okay. So that is what the problem. It is not that how much chlorine, how much elements are there, how much time it is taking. Okay. Covalent compounds are time taking. They have everything. There is no problem of the things. Okay. But only they take time. Okay. Now next is Lewis dot structure. Okay. So this is about the covalent compound only. So for Lewis dot structure, you have to have practice. Okay. So I will give you the practice sheet so that you can practice more number of questions and you should get a perfection. Okay, so here we will study the theory. The total number of electrons required for writing the structure are obtained by adding valence electrons of combined atoms. Okay, so I am teaching since years and every time they will ask, once I give notes, they will write. But after some time during the revision time, they will ask, sir, why this? Sir, like suppose H2O, okay? Then we will write 2 into hydrogen plus 1 into oxygen. Then I will write 2 into 1 plus 1 into 6. Then they will say, sir, it is spelling mistakes, sir, it is 16, sir. Actually, it is not mass number. It is the valence electrons. Okay. So total number of electrons are how many? 8. Okay. So first you should combine the total number of valence electron of all atoms. Okay. Hydrogen have only one valence electron. Oxygen have 6 valence electron. This is the first step to write the Lewis dot structure. Okay. This is the what? First step to write the Lewis dot structure. Okay. Now after combining, then what we should do, that we will come to know now. Okay. Distribute total number of electrons as a bond pair between atoms for the skeletal structure of compound known or is to be pre-assumed. Okay. So like we got 8 electrons. Okay. How many electrons? 8 electrons. That is to be, first of all, we should give them as a bond pair. Our first preference, try to accommodate all electrons to be accommodated as a bond pair. Once I say bond pair means that should be between the two atoms. So if I write electron between the two atoms, that is a bond pair. If I write that electron behind the atom, then it will be lone pair. So here question is, you should write them, first of all, try to write them as a bond pair. Then you can think of the lone pair. Okay. Now, as I told you here, it is pre-assumed. Okay. So how to pre-assume? That is also problem. How I come to know, sir, nitrogen should be at the center, sir. Okay. So then what, these are the rules. Okay. You have a problem, we have a solution. So out of the H and O, H2O, okay, oxygen valence is more. Oxygen valence is 2 and hydrogen valence is 1. So first of all, try to keep the more valency element at the center. That's why you will find oxygen at the center. Suppose in some cases, valency will not work. That time, like let us take NF3. Okay. So here fluorine can form one bond. Actually, it should be like other halogens are doing, like fluorine, bromine can form 7 bonds. But fluorine, because of its personal problem, what is the personal problem? Ego problem. Okay, it is highly electronegative. Okay, it never want anybody to ask him electron. So it will always take maximum 1 electron only, and it is not that it will ask lakhs of electron. It will ask only 1 electron, therefore one bond. So nitrogen is to be placed immediately at the center. Okay, so like that, by using simple common sense, we can pre-assume which is at the center, which is the peripheral atoms. Okay, so single bonds are constructed first with bond pairs. If the remaining electron pairs are utilized either in multiple bond or remain as a lone pair. Suppose nitrogen, okay, in NH3. In NH3, How many valence electrons are there? Nitrogen have 5 valence electron, 3 hydrogen have 3 electrons. So total will be 8 electrons. So first of all, try to give them as a bond pair between the atoms. Okay. And if they are left over, then I am giving them as a lone pair. See here, nitrogen is fully satisfied, hydrogen is fully satisfied, hydrogen fully satisfied, hydrogen fully satisfied. If electrons are left over, but why I am not using as a multiple bond? Because they are night hydrogen cannot form multiple bond. It is can form only one bond. If there is any chance, then I will try to substitute those electron in the multiple bonds also. Okay, so first try to add the all electron, then try to accommodate in the bond pair. If bond pairs are over, then you will go for the lone pair or multiple bond. And for making the skeletal structure, try to keep the atom with more valency at the center. Okay. So this is what the Lewis dot structure. Don't forget to solve more and more questions of Lewis dot structure. Okay. So here formal charge. Next topic is formal charge. Okay. So in the formal charge, it is only formality. Actually, it does not exist. Okay. So in chemistry, the main thing is there is sincerity. Whatever our chemistry teacher said, that is there in this things also. Like formality only. Actually, if you find, you will not get that. Okay. So formal is factor based upon the pure covalent bond formed by the sharing of electron pair equally by the neighboring atoms. Okay. Or it can be simple words, it can be regarded as a charge of an atom molecule would have if all atoms had same electronegativity. Actually, it will not happen. Suppose H and Cl. So if it is a what do you call pure covalent bond, it is not pure covalent bond, it is polar covalent bond. Okay. So it may not represent the ionic charge. Okay. We write it as a partial positive, partial negative. So this is the representation by assuming it is polar covalent. Okay. That is a formal charge. Theory is not important in this one, but formula and questions related to them is important. Okay. In case of the polyatomic ions, net charge is possessed by the ion should be uh, not on a particular atom. Okay. So like if I say SO4 2 negative, so we don't know this 2 negative who is having. Okay. So in that condition, however, it is feasible to assign the formal charge. We will write the formal charge, then we will find out sum of the formal charge will be minus 2. It is not that 2 minus is directly available on one of the bonded atom. Okay. So here formal charge of an atom is polyatomic molecule may be defined as difference between number of valence electron in an isolated or free state and number of electron assigned to the atom in the structure. So before going for the bond formation, how many electrons it is having, and after the bond formation, how many electron it is having. Okay. So like IT income tax. Okay. So before this financial year, how much you have, and after this financial year, how much you have. The difference shows your income. Likewise, any atom before going for molecule formation, we will take. Then after molecular formation, we will take. The difference is called as a formal charge. Okay. So here before it is isolated atom. Sulfur is first isolated atom. Then it is participating with the bonds in four oxygens. Okay. So that is a formal charge. Okay. That is theory part. But if you understand that theory part only, you can use this formula efficiently. Okay. So otherwise you have to cram the things. So first QF formal charge. QF means what? Formal charge is equal to Na minus Nm. Okay. So what is Nm basically? Nm is the number of electrons belonging to the atom in the molecule. That means that is invested in the molecule. Actually, any atom will invest the electron as a form of the lone pair, as a form of the bond pair. Okay. So this is originally it is having. This is happened after formation of a molecule. Okay. So lone pair is a whole and sole property of that atom. So we cannot give it to anybody. But bond pair only half of the electron belongs to it and half electron belongs to the other atom. Okay. So let us take suppose nitrogen. Okay. The NH3 only. So in NH3, these are the 5 electron. Okay. These are the 3 electron. Now, so here nitrogen is originally having 5 electron before bond formation. But after that, how many are there? 8 electrons are there. Okay. So when I count the circle in the nitrogen, electrons in the circle of the nitrogen, you will find 8. So this 8 is the Nm. Okay. Originally by birth it is having 5 valence electron. Okay. So that extra electron. Okay. So how they got? They got due to the lone pair and bond pair. Okay. So here it will be 8 electrons. See number of lone pair. How many? Lone, not lone pair actually. This is also misunderstood. Lone pair electrons. Okay. Minus. Okay. Number of lone pair electrons are how many? 2. And out of this 6 are there. But it will be 3 only. 3 only. Why? Because out of this 6, only 3 belongs to it. Remaining 3 are given by the hydrogen. Okay. So that means 5 electron is still having in the molecule also. Okay. So out of this 8 electron, 3 are given by the hydrogen. It is not his property. Okay. So the number of electrons in the bond pair. Why it is half? I think it is clear now. During bond formation, both will provide one electron. So 2 electrons are not a sole property of each and every atom. It is half only it is eligible. Okay. So let us take the Lewis dot formula. Example if we take, then it will be comfortable. Okay. So if we take pH3 as an example and solve, then you will come to know. Okay. So this is the Lewis dot structure of pH3. Okay. So I will draw the circles type. Okay, this is a circle of the phosphorus. It is having octet, and this is a circle of the hydrogen. It is also having duplet. Okay, it is also having duplet. Duplet for the hydrogen, octet for the phosphorus is our motto. Okay. Now, number of electrons in atomic state. How many? 5. Okay. So Na is equal to 5. Lone pair electrons. How many? 2. So NLP is equal to 2. Bond pair 1, 2, 3, 4, 5, 6. So half of the 6, that is 3. So 5 minus 5, 0. That means net income of the phosphorus is nil. Nil bata sannata. In Hindi it is called as a nil bata sannata. Okay, P is equal to nil. That means there is no charge on the phosphorus. Now let's see anything is gained by the hydrogen. It should not be, because as a total it is neutral. So if it is not having charge, then it is also not supposed to have any charge. So here nitrogen from by birth having how many electrons? Only one electron. So Na will be equal to 1. Lone pair, it cannot imagine also. Already God gave on one electron, and how you can imagine lone pair. Okay. So 0. And half of by where 2 electrons are there, half of the 2, that will be 1. So 1 minus 1, it is 0. So the formal charge on hydrogen also 0. Is it understood? This is how you will calculate the formal charge, and this also requires practice. I will give you one practice session. Okay. So then what is the use of finding the formal charge? Actually, so the it gives a tendency. Is it having a capacity? One find a, it is required. As of now, it is not required. But if any time it is required, okay, then what happens? So to build up positive or negative charges. Okay. Then lowest energy structure is one with the smallest formal charges. Okay, smallest formal charge is there, then it will be lowest energy. Most stable structure is one which have the smallest formal charge. That means it is first used to find out the compare the stability. Okay, then compare the energy, understood, and the ability to form a or build up a positive ion or negative ion. These are the three applications of formal charge. Okay, now I think it is clear. Now let's see this is all about the covalent bond. Okay, covalent bond definition we have studied. Okay, where it represents the sharing of electron. Then types of covalent bond, pure covalent bond and polar covalent bond. Then factors favorable for covalent bond we have studied. Then we have studied about the properties of the covalent compounds. Okay. Then we have studied the Lewis dot structure. Okay. Then we have studied the formal charge. Now it's time for the ionic bond. How ionic bond will be formed. Okay. So a strong electrostatic force of attraction between two oppositely charged. Okay, strong electrostatic force of attraction between the two oppositely charged ions formed due to transfer of electron is called as ionic bond. Okay, so one will form positive ion by losing, another will form negative ion by gaining, then there will be attraction between them. Okay, because one is helping and another is taking help. Okay, so generally ionic bond is formed between group 1 and 2. Okay, it will lose one electron, it will lose two electron, and 16 and 17. Okay, it required one electron, it required two electron. Okay, so like this electron will be transferred here, octet, octet. Same way here, one electron is transferred here, octet, octet. Okay. So because one atom and vice always coordination, sorry, ionic molecule formation, ionic compound formation is a redox process. Because once it loses electron, then it will form as a cation, and it gains electron, it will form as a anion. Likewise, it is everywhere required. What is there? It is everywhere required. Okay. Then factors favorable for formation of ionic bond. Similarly, we have studied in the covalent bond also. Okay, that opposite where it is to be. There we studied high ionization potential so that it should not have any option to think. But here we will give option to think. Okay, so first of all, low ionization energy, then only it will think to lose, then other person will try to gain. Okay, so atoms having very low ionization potential forms cation very easily. Okay, like ionization potential of potassium is 495.57. Therefore, it will lose electron more readily. Okay, even compared to the sodium. Sodium is for 519.82. Okay. Now, see here, sodium forms very easily cation because it have to lose one ion. Then there is no chances of covalent. Obviously, it will go for the ionic, okay? But aluminium will think twice or thrice because to form a complete stable and cation, it have to lose three electrons, okay? So it have to lose only two electron. It have to lose only one electron. Therefore, formation of sodium cation is very easy when compared to formation of aluminium. Okay, because it have to lose three electrons. It have to lose how many? Three electrons. Okay. So first factor favorable for cation is it should be less number of electron it should be able to lose. Like aluminium have to lose three electron. Then there are less chances of cation formation. Sometimes it will think to share the electron. Share electron means covalent bond. So small charge is favorable for the ionic bond. Then large size should be there. Okay. Large size means so many electrons are there. Cesium have so many electrons. So losing one electron, it will not think. But lithium have only three electron. If somebody asks electron, then it will think. Okay. So therefore, it have less tendency to form cation. It have to more tendency to form cation. Okay. Then formation of cation with inert gas configuration. Okay. So everybody will think, if I give electron, what is my status? Okay. So if after losing the electron, if it becomes more stable, then definitely it will try to give with full interest. And interest is always in the inert gas configuration. Okay. So like calcium also gains electronic configuration octet. Okay. And zinc as actually it got the pseudo octet. So pseudo octet are less interested, less stable. Okay. So that's why calcium 2 plus more readily gives, because it is going to get the wonderful stability. And zinc will think lose electron also, still you are not getting much stability. So that means less chances of losing. That means less ionic character. Okay. So why zinc have less ionic character with comparison to calcium? Because it is not, there is no much impurity, much improvement in the stability. Okay. Okay, now let's see the next one. Factors favorable for anion formation. Factors favorable for what? Anion formation. Okay. So high electronegativity. Okay. Factors favorable for anion means electron should be gained. So gaining tendency will be there when it is highly electronegative or electron affinity. So fluorine greater than oxygen greater than nitrogen. Next, small atomic size. Then only nucleus will effectively attract the electron. Then low charge on anion. It should be able to fulfill its need with few electron only. So fluorine gets the octet only just by the loss of one electron. But oxygen have to, gain of one electron. Oxygen require two electrons, so it is a time taking process, because every person may not be able to give two electrons. Like if the oxygen asks sodium electron, it can give only one. Okay. So but fluorine immediately it will transfer, because it can lose one electron and it want one electron only. Okay. So formation of anion have inert gas configuration will be easy. That means after gaining electron, if it is able to form inert than pseudo inert, okay, then that will be the best idea. Okay. So these are the factors favorable for cation and anion. Cation, small positive charge, large cationic size, and getting the inert gas configuration. Same way anion, high electronegativity or affinity, small atomic size, low charge, and ability to get inert gas configuration. Okay. So these are the things favorable for ionic. But once it is strong cation and strong anion, obviously strong ionic bond. Okay. So this is just a summary and a series or comparison or uh, increasing orders. Okay. So suppose element A have less electronegativity and element B have high electronegativity. Okay. Then less electronegativity will lose, high electronegativity will gain. Therefore, there will be ionic bond formation. Okay. If both are electronegative, that means both are non-metal, so nobody want to lose, then obviously what they will go for? Sharing. So there will form the covalent. If both want to lose, then who will take? Nobody will take. Therefore, it will form a C. Okay. So then metallic bonding. Okay, for example, NaCl, KCl, RbCl, CSCl. CSCl is readily formed because of the large atomic size. Because of what? Large atomic size. Cesium ionization energy is low. Therefore, it is readily formed. Okay. Same way sodium fluoride, NaCl, NaBr, and out of these three, which is readily formed? NaF will be readily formed because fluorine can have electron easily among NaFCSF MgO. which is readily formed cesium fluoride, because cesium is ready to give electron easily, fluorine is ready to take electron easily. Therefore, a CSF will be formed easiest manner. Okay, so this is the ionic bond formation. Okay, next let us see Fajans rule. Very important rule. Just now I explained also in one of the point by taking the Fajans rule. Okay, now it is clarified and completely detailed explained. Okay, so Fajans rule. No bond is 100% ionic in nature. No bond is 100% ionic in nature. Okay, every bond have some percentage of covalent character. In this universe, no substance is pure. There will be some or impurity will be there. So, but there are certain some less impurity, sometimes it will be more impurity, but impurities will be always there. Okay, if 100%, if anybody says 100% genuine, so that means he is 100% wrong. Okay, because there is no 100% in the world. Okay, so why it is, on what basis we will say covalent character is more, on what basis we will say ionic character more? There are two bases. How many bases are there? Two bases. Okay, first one is polarizing power, second one is polarizing ability. Okay, so what is polarizing power? Polarizing power is the ability of cation to polarize the nearby anion, is called polarizing power. Okay, so what does it mean? That I am telling you here. Um, so this is cation. Okay, initially everybody will try to think that I will give my 100%. Okay, just like the students in the 11th class, as soon as they get mark sheet, they get results of the 10th class, they will feel that now I will work sincerely from the day one. But slowly, slowly, that interest, ability, agility, everything will go down. Okay, so same will happen with this also. Initially, it is 100% ionic, but this anion have some cute electron. What electron? Some cute electron, extra electron. This is the extra electron. Okay, so once it start revolving, then it will think, "Arey, why I have given that electron to him? I should have keep it with me only. She is so shining. When it was there with me, it was not shining." Then it will start pulling that electron towards itself. Okay, being a metal, it should not do like that. Okay, so it is losing means by in the Josh it have given the electron. After that, it will feel that array I should take it back. Okay, so in that taking back, it will pull this total orbital towards itself. Okay, towards itself. So because of this, see, earlier it was exactly circular. Now it is deformed. Okay, it is becoming as a something what you call like this. Okay, it is not circle. Now earlier it was exactly circle. Because of this attraction, this it is deformed. Okay, so that deformation is only called as a polarizing. Okay, so that tendency, how much it can pull towards it, that is called as a polarizing power. Who will do that? Cation. Okay, so polarizing power is basically assessment of cation. Okay, and polarizability, it is ready to pull, but it should also be ready to lose. If it is very strict, no, I don't want to give my electron, already you have given it to me, so no more authority is there on this electron. That means it is polarizability zero. Okay, you can take it as it is your electron only. That means it is polarizability is more. Okay, so the tendency of anion to get distorted or polarized by the cation is called as a polarizability. Okay, so that means it should be ready to get polarized, and it should be ready to polarize. Okay, so in Hindi there is a kahavat, do haath se थाली बजती है. Okay, so that means this is also should be capable of polarizing, and this is also should be ready to get polarized. Okay, so that then only this polarization will takes place. See, once we say it is polarized, see there is a overlap. Overlap means which bond? Covalent bond. Okay. So initially it was 100% ionic. Slowly, which properties are getting inside? It is getting to going towards the covalent bond. Okay. So simple two things you should remember. Initial condition of the Fajans rule, it will be 100% ionic. Slowly, it will tend to the 100% covalent. Okay, extreme condition of the Fajans rule is covalent. Initial condition of the Fajans rule is ionic. Okay, so according to him, so when polarizing power of the cation and polarizability of the anion increases, polarization increases. Okay, so that also I will write it here. Okay, polarizing power of the cation increases, polarizability of the anion increases. It will result in the polarization. Okay, so polarization increases, that means overlapping will be increases. What increases? Overlapping. Actually, overlapping is a pure property of covalent. Therefore, covalent nature increases. Okay. Covalent increases obviously from where it will increase by decreasing the ionic nature. Okay. So this is the gist Guru mantra of the Fajans rule. Okay. So if you remember this, nobody can beat you in the Fajans rule. Okay. So now how to compare which is more polarizable, which is more polarizing power. Okay. So first of all, polarizing power increases the covalent character. Okay. Um, See here. Let us see the previous slide. One thing is missing. Okay. So here written that polarizing power directly proportional to charge of cation. Once we are talking about the polarizing power, we should talk about the cation. If we talk about the polarizability, then we should talk about the anion. Okay. Then inversely proportional to size. Small atom can polarize better and more charge can polarize better. Suppose if you ask Na plus and Mg2 plus, okay, so its polarizing power is more because charge. Okay. If you ask sodium plus and potassium plus, so then sodium can polarize better because of its inverse proportional to charge. Okay, so this is the first comparison parameter of the uh, ionic and covalent character. Okay, now let us see the ionic with respect to polarizability. We have seen with respect to polarizing power. Now with respect to polarizability of anion. So more charge, more will be the attraction. Suppose here one anion is there with one electron. Okay, one cute electron only it is having, and another anion is there. Another anion is there, it is having how many electrons? Two cute electrons. So definitely who is getting polarizability more, this will be more chances of polarizing this only. Okay. If some metal comes to polarize, definitely it will try here only, not here, because it knows two electrons are there. That means two negative is there. And here two electrons are there, but nucleus is nearby. Okay, what is nearby? Nucleus is nearby. Okay, this Fajans rule. For cation, it should be for cation, the charge should be higher one, and for anion, charge should be lesser one. Okay. Okay, here if we take the first example, okay, total polarizing power and polarizability on this combined, if the question comes, you should be ready to pick, okay. So let's suppose if the question is arrange the following in increasing order of covalent character. So we should be able to check that chlorine is common. So then question is of the this sodium, magnesium, and aluminium. And we have seen aluminium is +3 and sodium is +1. Okay, so cation means use the rules of cation. See here we have said polarizing power directly proportional to. Okay, polarizing power just now I told you direct proportional to charge. Okay, now using this rule in the next slide. See here. The next slide, aluminum is having more positive charge. Okay. So more positive charge means polarizing power increases. Polarizing power increases, so covalent character increases. This is what it is written. So AlCl3 is more covalent. Sodium chloride is more ionic. Okay. So, but same question if it is asked like this. Here aluminum is common. So question is about the halogen. But in halogen charge is same. Then what you will use? Size rule. See here. Negative ion use polarizability. Size increases, polarizability increases. So more polarization will be there in the I minus. So more covalent character will be there in the I minus. AlI3 more covalent, AlF3 more ionic. Understood? So next, sometimes there is a chance of the pseudo inert gas configuration also. CuCl is more covalent. Okay. So this is very important for the advanced examination, AIMS examination. Cation with 18 electron is having greater polarization, therefore greater covalent. Like Cu after losing one electron, it will have 18 electrons. But sodium after losing one electron will have 8 electrons. So whichever is having 18 electron will be more covalent, which is having 8 electron will be less covalent. Okay. So this is how you have to arrange the things in the Fajans rule. Okay. Fajans rule is very important and you will get question in terms of the orders. Covalent character which is having more, ionic character which is having more, like that. Okay. Okay, so this gist of this ionic character and covalent character is here in the periodic table. So on moving down the group, polarizing power of cation decreases. What is the reason? Size increases. Size and polarizing power inversely proportional. Okay, in period, polarizing power increases because size decreases. Okay, size decreases, polarizing power increases. Okay. Then polarizability of anion decreases from left to right. Here also same. Size is decreasing, polarizability also decreases. Okay, that directly and inversely, if you are perfect, you can write anything. Okay, then polarizability of anion increases top to bottom. Okay, that is in the group size will increase. Size will increase. That's why polarizing ability increases. Okay, increasing polarization means more covalent and decreases ionic. Okay, then increase in covalent character indicated by decrease in melting point. More covalent, less melting point. Okay. So melting point also can be used to judge the covalent character. Okay. So this is about the Fajans rule and its variation of the covalent and ionic character in the periodic table. Okay. So special point to note. Okay, that is what I told you. Pseudo inert gas configuration is there. Then definitely covalent character will be more. Okay, this is very important point. Okay. Okay, by using the electronegativity scale also we have identified. Okay, if electronegativity difference is 1.7, exactly 1.7, 50% ionic, 50% covalent. If electronegativity difference is greater than 1%, then ionic is predominating. Less than 1.7, then covalent is more predominant. Okay, but HF is exceptional where even though it is having 1.7 difference, but still it is covalent only. Okay, so this is the application of what? Fajans rule. Very important. 1.7 is very important. Okay, more difference, more ionic, less difference, less ionic. Okay, after the Fajans rule, next topic is lattice enthalpy. This is very small topic and very easy topic when compared to the Fajans rule. And mostly there will be increasing order, decreasing order and solubility. Interrelated topic are increasing order of stability, increasing order of ionization energy. So increasing, decreasing order questions will be there and solubility will be there. Solubility is linked up with the hydration enthalpy. Okay. So first of all, what is lattice enthalpy? Then you will connect this topic with the frequently asked questions. Then the amount of energy released when the number of oppositely charged gaseous ions present at infinite distance come closer or to form 1 mole of ionic crystalline solid. So let us take sodium positive. Sodium positive is in gaseous state and same way chlorine negative is in gaseous state. So they both of them join together to form the NaCl solid. So that time whatever the energy released, that released energy is called as a lattice enthalpy. Okay, so now if you read then it will be easy. The amount of energy released, this is U. Okay, when required number of oppositely charged. In case of the NaCl, only one sodium positive, one chlorine negative is required. Sometimes it may be more than also, but we should make sure that number of moles formed will be always, this should be 1 mole. It can be any number, it can be any number, but number of ions, there is no restriction. Number of substance formed mole should be 1. Okay. Oppositely charged ion present at infinite distance. This is far away from the Cl minus. This is far away from the sodium plus. And to form, come closer to form 1 mole of crystalline lattice. Now see here, this is solid state. Okay. So in chemistry, until unless you don't minutely observe, it will not be affecting you. Okay, it will not be effectively understood. So lattice energy is directly proportional to product of, so Z positive and Z negative. It is just like a physics only. So attraction force is equal to Q1 Q2 by D. Okay, so same way Q1 Q2 here, positive charge and negative charge, and inversely proportional to sum of the radius. Okay, that is distance only. So when two ions are approaching, there is a close approximation. So that is the R positive ion and R negative ion, where Z positive and Z negative are the charges. So based on this, sequences will be coming. I think now it is lattice enthalpy topic is clear now. Now let's use it in the orders. Okay. So first part topic is Born-Haber cycle is used to calculate the lattice energy. Okay. So what is Born-Haber cycle? Initially, we will have sodium solid and we will have the chlorine gas. And ultimately, we should form the sodium chloride solid. So during this, chlorine is to be dissociated into two chlorine gas. Then you have to add one electron. Then it will form as a Cl minus. Then gas. Okay. Then this gaseous ion is ready. Same way, sodium gaseous sodium solid will be converted to sodium gas because for ionization energy in the periodic table we have already studied. The ionization energy definition itself says that amount of energy required to remove most loosely bound electron from isolated gaseous ions. So here it is need to be made it as a gaseous state. For that sublimation energy. Okay. And then if you give the ionization energy, it will give you the electron. So then it will form as a sodium positive in gaseous state. So it is in gaseous state, chlorine minus is in gaseous state. Then the resultant energy will be calculated practically. Then you lattice energy will be calculated. This is called as a Born-Haber cycle. Okay. Now orders here. Already told you lattice energy directly proportional to Q1 positive charge, Q2 negative charge distance. So here what is the basis? Here all are having plus minus, all are having plus minus. That means the question is not about the numerator. Question is about denominator. Okay. Question is about what? Denominator. Here the radius is decreasing. So radius decreases, then the closest approach will also decrease. So lattice energy will be increasing. That means lithium fluoride, due to smallest cation, the closest approach will be maximum, and ionization energy, sorry, lattice energy will also be maximum. Smaller the cation, smaller the anion, larger will be lattice energy. Same way lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Here, in keeping the cation constant, what they are changed? They have changed the negative ion. So once they change the negative ion, obviously we have to arrange them according to the smallest anion, largest lattice enthalpy. Okay. Now you see these two concepts are combined together and merged with the charge concept also. See here, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. Charge is increasing. So charge Q1, Q2 both are increasing. Even 1 also increases, it increases. Now here it is, both are increasing. So lattice energy will be obviously increases. Okay. So these are the lattice energy factors and some series. Okay. Then greater the lattice energy, more is the strength and low solubility. This is what I told you. The same thing can be used with the solubility also. So aluminum nitride is less soluble, sodium fluoride will be more soluble. Lithium fluoride will be less soluble, potassium fluoride will be more soluble. Lithium fluoride will be less soluble, lithium bromide will be less soluble, more soluble. Okay. So simple. First you will identify on which factor you will find out lattice energy, whether it is on the size or charge. Size it is inversely proportional, charge it is directly proportional. Once you calculate the lattice energy comparison, then lattice energy increases, then solubility decreases. So these 2 points only most of the questions are coming. Okay. So when cation, anionic or in gaseous state interact with solvent in liquid state, the energy will be liberated. Always lattice energy will be liberated. Okay. That is also called as a solvation energy. In case of water, it is called as a hydration energy. Okay. That released energy must be, that hydration energy, whatever it is releasing, that must be able to break the ion charge, sorry, attraction force existing between cation and anion. That is that cation and anion lattice energy. Okay. So that means for anything to be soluble, released hydration energy must be more than the lattice energy. Released hydration energy must be more than the lattice energy. Then only it will be soluble. Okay. So when solvent is water, liberated energy is called as a hydration energy. And the value of solvation depends on size and solvation energy. Okay. Same factor on which our lattice energy depends, almost on the same factor. Total hydrogen energy also depends. Okay. So these are the some ionic compounds. Okay. And some terms related to ionic compound. Now we will start with the properties of ionic compound. Ionic compounds, first of all, are solid. In the covalent compound, I have said you already, the exceptionally polymeric solids, polymeric network, then it will be solid. Otherwise, it will be liquid and gas. But in covalent, you will find almost all type of physical state. Solid, liquid and gas. All the states you are getting. But in case of the ionic compound, you will find only one solid state because strong electrostatic force of attraction. Then they are generally soluble in polar solvent. Ionic compounds are soluble in polar solvent. Okay. Then solubility of ionic compound decreases with increase in covalent character. Okay. So lesser covalent, more ionic, therefore more will be the soluble. This I am talking about the water. If it is in the non-covalent, then inorganic. Okay. So generally higher the lattice energy, lesser the soluble. That is what I told you. Sulfates, phosphates of barium sulfate and strontium are more soluble due to high lattice energy. Okay. Due to what? Lattice energy. Is it understood? Okay, higher the lattice energy, then it will be very difficult to break the existing bonds. Therefore, solubility will be less. Okay, so for simple solubility, three factors. Most major factor, solubility of ionic solvents inversely proportional to lattice energy. Okay, directly proportional to dielectric constant of solvent and directly proportional to hydration energy. So question will be framed on either of the three. Only one they will take. Either that question will be of hydration energy or dielectric constant or lattice energy. Suppose question is NaCl is highly soluble in water but not in benzene. That means that question is based upon the dielectric constant. Okay. So here one more example, sulfates and phosphates of barium and strontium are insoluble in water due to high lattice energy. Okay. So more heat of hydration, more will be solubility. See, aluminum chloride actually it is covalent in nature. There is a sharing of 3 electron by the aluminum with the 3 molecules of chlorine. Okay. So therefore, 3 chlorine ions. Therefore, heat of hydration will be excellent. So due to high heat of hydration, see this is a heat of hydration energy increases, solubility increases. Okay. So these are the three very important factor on which mostly you will get in the S block, P block, D and F block also. Solubility questions will be of them, but base you will study here. That's why for smooth inorganic, we have to be very perfect in chemical bonding, redox reaction and periodic table. Okay. So more heat of hydrogen then ionic compounds are good electrical conductors. Now most of the people study up to here and leave it. Actually electrical conductors is due to, okay, is due to flow of ions. Is due to flow of ions. Okay. And there is a minute difference between molten state and aqueous state. Okay. So when I say NaCl liquid, that shows it is molten state. NaCl aqueous, that shows it is aqueous state. It is impure state of the sodium chloride. Here you will find in water also. And here you will find only sodium plus chlorine minus ions. Okay. So these minute things are very important for future understanding. Okay. Now let's see the next one. Okay, the ionic compounds undergo quickest. Okay, already I have told you with one of the example also. In ion covalent compound, first of all, they have to form ions, then they have to go. Here there is no problem. Already they are ions, immediately they can exchange. Okay, that's why the quickest reactions are from the ionic compounds. Okay, now let us see the next one. NaCl ionic compound do not exhibit isomerism, but they will show the isomorphism that I will tell you afterwards because non-directional. Actually, isomerism is due to difference in shape. So, but there is no in one direction. Like if we say CCl4 is tetrahedral, but there is no shape for the NaCl like tetrahedral, octahedral, linear, because sodium charge will be uniformly spread throughout in 360 degree in sodium plus. Same is the with chlorine minus. Okay. So the melting and boiling points of ionic compounds are very, very high. Melting and boiling points of ionic compounds are very, very high. Okay. Then if the anion is common ionic compounds, more ionic compound, more cations having high atomic weight will have the more melting point. Okay. Suppose negative ion is same here, Cl2, Cl2. Okay. Then the compound with cation having high atomic weight. Here atomic weight of barium is very much high and atomic weight of beryllium is less. So its melting point will be very much high. Okay. So this is about the some properties of ionic compound. Same way melting point of cesium greater than lithium fluoride. If cation is common, then compare with the lattice energy. Okay. Don't compare with the molecule. Very cute and small and very Important. If cation anion is common, then compare with the mass of cation. But if cation is common, okay, then compare with the lattice energy. Then they will have the higher melting point. See, sodium fluoride and sodium iodide. Okay, anyhow, both are directly proportional, but sometimes it makes a difference. Okay, so sodium cation is common, anion is different. Then lattice energy will be more in NAF due to, here we cannot say size or mass. Okay, here we can say that sodium fluoride is small, having lattice energy high. Okay, so higher the lattice energy, higher will be the melting point. But according to this should have the size or mass, it should have the less melting point. Okay, so that is a small difference, but mostly you will get the negative marks if you don't study. Okay, so let us see the next factors or next characteristics. Okay, isomorphism. Just now I told you there is no isomerism in ionic compound, but they show instead of ionic isomerism, they show another type of process which is called as isomorphism. Okay, isomorphous means due to similar electronic structure, they are isomorphous. Like sodium fluoride. Sodium and fluorine will have the eight electrons in their valency shell and only one inner core. Okay. Same way here also inner core. Okay. Same way that means sodium fluoride are isomorphous to magnesium oxide. Here K2S and CaCl2 also isomorphous. Here sulfur will be attracted by the both sodium potassium and all of them are have same structure. Okay. So that's why they are called as a isomorphous. What they are called as isomorphous. Electronic structure must be the same. Okay. What must be same? Electronic structure must be same. Okay. Next one. Bond length. Okay. Now we are in the topic of bond parameters. Okay. Actually, I forgot to write the heading. Here the topic is bond parameters. Okay. Bond parameter means whenever there is a chemical bond between the two atoms, there are something specifications. Like before you purchase a laptop, then you will ask what are the specifications. Like that, before assessing something about any bond, okay, before something Okay, so before assessing something about the bond, we have to write the specification. Okay, so like laptop specification, computer specification, we will write about the RAM and processor and internal memory. Okay, extendable up to like that, and screen touch screen or not, HDR not like that bond. Similarly, we have to write some parameters about the bond also. Okay, so that parameter in what way you will write? Okay, first you will write about the bond length. Okay, then we will write about the bond energy. Then we will write about the bond angle. Then we will write about the bond order. Okay, these four are collectively called as bond parameter. Bond parameter, now I think it is clear. So one by one we will be discussing. Okay, most conceptual topic of the total chemical bonding, and every group of the periodic table will have one question related to this. Okay, so that logically explanation I will give you, so that main thing is people are just cramming only definition and going, but how the questions are coming, how we have to face them, process I will tell you. Okay, So bond length is the equilibrium distance between. Actually, it can be average also. In some books, it is mentioned as a average distance between nuclei of two bonded atoms in a molecule is called bond length. Okay. So bond length is measured by spectroscopic X-ray diffraction or electronic diffraction techniques. So how many methods are there? Spectroscopy, second one X-ray, and X-ray diffraction, third electron diffraction. Okay. So already we have studied in the uh, periodic table, every element radius is different method we have to adopt. Out of this, most and frequently used are covalent radius. Okay, covalent radius. Second one is what is called as uh, metallic radius. Okay, then radius is called as a van der Waal radius. Like that, three radius are there. Now we will consider the covalent radius. Covalent radius of an atom homodiatomic molecule AA type. Simple diagonal, okay, sorry, diameter divided by 2 will give you the covalent radius. Okay. So that half of the 2 diameter. Okay. I will tell you like this. Then it will be very clear. This is very identical homoatomic. That means both are chlorine only. Suppose total distance we have, this is the total distance. Okay. Actually, bond length is the distance from the center of nucleus of bonded atom. This is one nucleus. This is another nucleus. This energy, this distance we want. Then what we will do, we will calculate the D here. Okay. And here it will be D by 2. Here it will be what? D by 2. Okay. So that is what bond length measurement. First parameter of bond is bond length. Okay. Now this is not much important. The important topic is how, on what factor it will vary and how you will approach. Okay. But for understanding them, at least basic knowledge I have imparted to you. Okay. So if covalent radius of heterodiatomic, then problem is there. Okay. Then calculated by, okay, calculated by simple radius of cation plus radius of anion plus C into electronegativity of A and B. Okay. Electronegativity of A and C depends upon the type of atom that you will, that is, you can treat it as a constant, you will be given with that. Okay. So don't think that in heteroatomic simply add both cation and anion. If electronegativities are given, you have to utilize with the constant also. Okay. So next, bond length between set of atoms of different molecule. Set of atoms in different molecule always same. Okay. So here as the P character, okay, first characteristic is C. That's why we take it as average bond length. OH bond length in H2O in same, okay. It is between the oxygen hydrogen, it is between the oxygen and hydrogen, it is between the oxygen hydrogen, okay. Then is 0.97, okay. Then as the P percentage character of hybrid orbital changes the bond length, okay. See here, this is ethane, this is ethene, this is ethine. Okay, so in ethine, the hybridization we will come to know sp hybridization. It is sp2 hybridization. Here it is sp3 hybridization. Okay, so if I say ion p percentage character, here I will write sp, sp2 and sp3. Okay, so s percentage character, p percentage character. So total number of hybrid orbital are 2. So S percentage will be 50%. Okay, here P percentage will be again 50%. And sp2, S percentage will be 33.33 because out of the 3, our S orbital is 1, 33.33. Then P will be remaining 60, 5 or 66.7. Okay. So sp3, S is only 1. So 25%, remaining 3. that is 75% are sp3 orbital. Okay, in this way what you can do, you can find out the hybridization with the s percentage character also. Okay, so and coming to the bond length, how it is going to affect our bond length. S percentage character increases, bond length decreases. P percentage character increases, bond length increases. Okay, clearly I will write bond length directly proportional to P percentage character, inverse proportional to S percentage character. In ethine, 50% S percentage character. Okay, therefore bond length will be very small. Okay, and P percentage character maximum in the 25%, it is in the sp3. Okay, P percentage character will be 75%. So sp3 bond length will be P percentage character increases, bond length increases. Okay, these are the factors, definition, and units also very simple. It is a distance. So distance unit will be picometer, micrometer, nanometer, etc. Okay, now let's see the next one. Bond enthalpy. Okay, what is the next one? Bond enthalpy. Okay, next bond parameter is bond enthalpy. Okay, if you feel very problematic with the high-fi words, actually it is in the normal terms, bond energy is only called as a enthalpy. So bond energy, bond enthalpy, there is no difference. Okay, just to demotivate you, discourage you, they give like this. Okay, so amount of energy required to break 1 mole of bonds of particular type. Suppose hydrogen, hydrogen, there is a bond. Now there is no bond. Okay. So, and units are in kilojoule per mole. 1 mole of bonds for breaking these many kilojoules are required. See here, HA. It is also called as enthalpy of atomization. Okay. And it will be again used in the thermodynamics also, enthalpy of atomization. But for the time being, you will use it as energy only. That means to break 1 mole of hydrogen bonds, how much energy required? 435.8 kilojoules of energy is required. Okay. So here see carbon only. When they are forming one bond, 341 only. Between the carbon, when there is a double bond, 610. When there is a triple bond, 828. Like that, once number of bonds are increasing, then bond energy also increases. What increases? Bond energy also increases. Okay. And at the same time, here see the number of lone pairs, bonded atom increases, bond enthalpy decreases. Actually, carbon is the simplest person in the world. It does not have any lone pair. Okay. And here see how many lone pair are there. Actually, nitrogen can form only 3 bonds. One lone pair is there. The worst situation is with the oxygen. What is that? 2 lone pair. And further worst will be there between the fluorine actually. Okay. So it won't form any further bond. Understood? So as the number of lone pair increases, bond enthalpy decreases. Okay. So if we do it as per the other way, actually carbon bond length is more. Okay. So energy should be less. Bond energy should be less. But because of this lone pair, actually this lone pair is very problematic. See, there will be repulsion between them. So always it will think that it is better to separate to avoid this collision between the lone pair. So number of lone pair increases, then bond energy decreases. Okay. First thing, number of bonds increases. See, bond energy I will write. Bond energy directly proportional to number of bonds. First factor. Okay. And second factor, inversely proportional to lone pair. Okay, more lone pair, less bond energy. With live examples I am giving you. Okay, so that you can understand the question directly and start solving them. Okay, in case of H2O molecule, In case of H2O molecule, the enthalpy needed to break two H bonds is not same due to the changed chemical environment. Okay, so in English, there is a saying, the person who could not learn from his own mistake, he will learn nothing. Like that, see, after losing the 1H plus, one hydrogen, for first hydrogen it is 502. Okay, so but for second hydrogen it is losing, it is learning from the mistakes. I should not give so much of energy, then it reduced its energy 427. Okay, so that's why we use the term average bond energy. Why? Because we don't know which is correct at what time, so better to take average 502 for the first bond and 427 for the second bond divided by 2. So the average bond energy. Okay, the magnitude of bond energy depends on size. Simple small bond very difficult, big bond very easy, further big bond very easy. Okay, bond energy is inversely proportional to size of the atom. Bigger atoms can break the atoms easily. Bond energy values are less for homolytic fission when compared to heterolytic fission. Homolytic and heterolytic, actually we will study in the organic, but I don't want that it should be postponed. Okay, so suppose these are the hydrogen atom, both are hydrogen atom only. If sincerely it takes its electron, if sincerely it takes its electron, then it is called as a homolytic fission. Both are getting equal number of electrons. Okay, then there is a heterolytic. Both electron taken by this hydrogen and this hydrogen could not get anything. Then it is called as a heterolytic. Okay. So this type of distribution is there. This will be very peaceful. So peaceful means less energy, okay? But here there will be some fight will be there. This hydrogen will oppose why I should give my electron to you. Even you are also hydrogen like me, like that, okay? So more energy required here, less energy required here. Homolytic fission and heterolytic fission. Is that clear? Now let's see the next one. Third bond parameter is bond angle. What we have seen? First we have seen the bond length. Second we have seen the bond energy. And third one we are going to see the bond angle. Actually it is a imaginary angle between the orbital containing bonding pair of electrons around the central atom. Our complex sign is called bond angle. Okay. Suppose this is a carbon. Okay, and it is forming one bond with this one, another bond this one. Okay, so this is one orbital overlap will be there like this. Orbital overlap will be there. So a line representing the overlapping, and that angle is called as a angle between those lines are called as a bond angle. Okay, so bond angle how they are determined spectroscopic. See, bond length units are angstrom, picometer. Bond energy units, mostly we will use kilojoule per mole, but sometimes we can use the kilocalorie per mole also. And bond angle it is there. Therefore, we will use degree and minutes. 109 degree 28 minutes. Okay. Sometimes they may use radians also. It is just like a mathematics angles only. Okay. Now see what on what factor bond angle depends. Understood? So bond angle depends on state of hybridization. Okay. As S percentage character increases. See here, this is S percentage character. Just now I told you SP hybridization. S percentage will be 50. Total 2 orbital are there. Out of this S is 50%. And here it is sp3. Total 3 orbital are there. Out of S is 1. So if you find out, it will be 33.33%. And here if you see, total 4 orbitals are there. In the hybridization I am telling you, oh shit, it is sp2, it is sp3. So sp3, one orbital is s orbital, total orbitals are 4. So if you find out, I am getting 25 and you are also should get 25. Okay. Now bond angle in sp3 hybridization is 109 degree 28 minute. How it is I will tell you once we discuss the hybridization. For the time being you should see in the hybridization S percentage, SP hybridization is there. That time bond angle will be 180 degree. Bond angle will be how much? 180. Here it is 120. So you can see here S percentage character decreased, bond angle also decreased. So bond angle is directly proportional to S percentage character. Also we can say inverse proportional to P percentage character. Okay. Then if the electronegativity of central atom decreases, see nitrogen is more electronegative, Sb is less electronegative, then bond angle will decrease. Okay. Provided hybridization is same. This you should do only after confirmation. Hybridization is same, number of lone pair are same. Okay, then you will apply this rule. Okay, then in case of atom remain same bond angle, increases with decrease in electronegativity of central surrounding atom. Here see twist is very good twist. Here central atom they are changing. Okay, but hydrogen is same. But see here central atom is same, but hydrogen is different. Okay, and very good exception here Ni3 bond angle will be very large because see everywhere it is nitrogen only. Everywhere it is nitrogen only. But in case of the fluorine, they are very too small. Okay, so they can stay together. Okay, but in case of the iodine, iodine is very big. It want more space. So it want more space. It want more space. So bond angle will obviously increase, and here bond angle will be less. That's why when peripheral atom size increases or electronegativity decreases, then what happens? Bond angle will increase. More size of the peripheral atom, more will be bond angle. Small size, small bond angle. Big size, big bond angle. That is what the care is. Okay, I think all of you understood now. Now let's go for the next explanation. Okay, three bond parameter we have studied and fourth bond parameter is here. Okay, what is bond order? It is simply number of bonds between the two atoms. This you will clearly understand when you go for the MOT. What is MOT? Molecular orbital theory. Okay. How to find out bond order, that I will tell you. Greater the bond order, more is the strength of the bond. Okay. More bonds obviously. If you put one stick, then less energetic. If you put two sticks tied together, then energy required to break is more. If you put three sticks and tie together, then energy required will be more and more. So greater the bond order, the greater is the strength of the bond. Okay, with increase in bond order, bond enthalpy increases. That means energy required to break will increase, and bond length decreases. One small bond length, what do you call, multiplicity increases, then they come closer. Okay, then isoelectronic species have same bond order. Here nitrogen there is a 14 electron, 6 plus 8, here also 14. 6 plus 7 plus minus 1, here also 14. All bond order will be same. And maximum bond order can be how much? It is 3 only. You will never find between two atoms more than 3 bonds. Okay. So that is given by the some theories. That theories also we are going to study. Okay. So 4 bond parameter I think now clear. The bond length, bond energy, bond angle, and bond order. Okay. Next, very important topic, very useful topic, especially not here, not in inorganic. It is useful in the organic. This is the only topic which is taught in the inorganic but applied in the organic. That is resonance. Okay. So resonance, physics resonance is different, quota resonance is different, and chemistry resonance is entirely different. Okay, so resonance means representation of a molecule in more than one structure, and none of them explains all properties of the molecule. Okay, of the molecule, then it is singly occupied. Okay, singly If it is singly represented, we are not able to explain its whole structure. Then that type of property is known as resonance structure. Okay. Okay, that means one structure is not enough. We have to draw more than one structure, and each one structure also not sufficient to explain all properties. Okay, suppose simple example I will take you. It is well known fact to everybody. Okay, this is a benzene. If I draw this structure, will I am able to all the properties explained? No. That time what I have to do? I have to write the one more structure also like this. Okay. So these two structures are necessary to explain all type of properties. So when a molecule is not happy with one structure, it want wide variety and not satisfied with none of them. Okay. It want this one also, it want this one also. Then it is called as a resonance. And each structure is called as a resonating structure and hybrid when you combine all of them and represent together like this. Okay, then it will be resonance structure. Understood? Resonance hybrid. So whenever a single Lewis dot structure cannot describe molecule accurately, then we will draw number of structure with similar energy. And in this one, very most important, never take out, never replace the atoms. Okay. Here atoms must be same. Bonding and non-bonding lone pair of electron also same. Okay. Then which describes the molecule accurately. Okay. So here I have not replaced the carbon. Carbon everywhere location is same. Hydrogen location is same. Total number of lone pair and pi bond also same. So such type of structures are called as a resonating structures. Okay, very important topic. So but it will be wide used in the organic. Okay, so now let's see the next one. See, this is a resonating structure of the ozone. Okay, after the benzene, the most important, most frequently asked question is ozone. Okay, so in this ozone, what is the resonating structure and how it is coming? They are all interconvertible. Okay, see, actually here it will be oxygen negative, this will be positive. Just we have studied in the formal charge. Okay, if you missed that, then you have to go again. Okay, this lone pair shifts here and this pi bond will come here. Okay, then this will be forming. Okay, after some time it will get bored about that, then it will shift lone pair to here and pi bond electron will come here. Simple, it is a game of lone pair to pi bond to lone pair. See here, lone pair to pi bond to lone pair, pi bond to lone pair to pi bond. Then once it is busy in doing the same job again and again, obviously it will be stress free. Okay, so more possible structure. Okay, then resonance hybrid of ozone. See here. Okay, according to this should be equal to double bond, this should be equal to single bond. But when they found it from the X-ray diffraction method, it is more than the double bond, less than the single bond. So that means it is resonant hybrid. Okay, so resonance hybrid, I think it is clear. So you should be able to draw the resonating structures properly with lone pair, pi bond and their location. Okay. Now, characteristics of resonance. Resonance, when more resonance is there, more will be the stability. Okay. So, if you are not happy with one, at least you will be happy with many structures. Happy means stability. Okay. More number of resonating structure, more will be the stability. Because of resonance, all bond lengths are become same. Just now I told you in the ozone double bond it is less than, but it is more than the double bond. So but when it is practically found, it is all equal just because of the resonance. Okay, so same way in benzene also all bond lengths are equal and real canonical form no existence. So when you ask this will exist, no, you will say no. When you ask the other structure, it will no, but it will exist in the both and keep on simultaneously moving from one structure to another structure. That is the characteristics of resonance. Okay. So let's see the next one. See, some rare resonating structures are inseparable. They are so busy in their converting one to another that if you wanted to separate them, you will not separate. Resonating structures are inseparable. Molecules such as a single structure in which resonate hybrid cannot act as such depicted by a single structure. Okay. Actually, we will write dotted line because sometime it will be double bond, sometime it will be single bond. Such structure obtained is called as a resonance hybrid, and this is very important trick. Bond order for polyatomic. Okay, if we have to find out bond order of two atoms, suppose O2, bond order will be 2. So that how you will find out by using the microorbital theory. But now what we are going to use is another theory. Okay. So what is that? Number of bonds between the two atoms in all resonating structure. You can pick anything. Okay. So you select one bond, then I will take that as an example. Okay. Now select. Suppose here we selected this one, okay? So here two bonds are there. Here between them how many bonds are there? One bond is there. Here how many bonds are there? One bond is there, okay? So then that is what I am explaining now. Here two bonds, here one bond, okay? Now total number of bonds between atoms in all resonating structures. So 2 plus 1 plus 1. And how many structures we have taken? 1, 2, 3. So divided by 3. That is 4 by 3. Okay, 4 by 3 means 1.33, I think it is. Okay, so bond order is 1.33. But what is bond order? Number of bonds. Okay. So is it understood now? So here number of bonds you have to take anything. Suppose if I take this one, now I will take another color and I will explain through that. Okay. So suppose this bond I will take every resonating structure, I will take that structure only. Okay. So total number of bonds are how many? One. Here between them one bond. Here between them how many bonds are there? Two bonds are there. Here between them how many bonds are there? One. Total resonating structures I have selected are three. So 4 by 3, that is 1.33. Okay. So like this you will calculate the bond order, and this is applicable when more than one resonating structure is there, polyatomic molecular ion is there. Okay. So I think all is this clear to you now? Okay. Okay, now we are into the next topic. Next topic is dipole moment. Dipole moment. Okay. What is dipole moment in chemistry? If you carefully study the name and understand the name, that itself is sufficient. Okay. What is that dipole moment is equal to? Di means two, pole means positive pole, negative pole, generated due to the movement of electron. Okay. So what is that? I will take some example with that. It will be clarified. When a covalent bond is formed between two similar atoms, hydrogen, fluorine, oxygen, is exactly between the two atoms. Okay. Suppose this is hydrogen, this is hydrogen. Okay. So they are sharing the electron. That will be exactly in between. But suppose hydrogen is sharing the electron with fluorine. Okay. Fluorine is very big atom. What it will do? It will pull this electron more towards fluorine, and hydrogen being small, very scary about the big fluorine. So it can't say anything. Then this will be partially positive, this will be partially negative. Such type of covalent bond is called as a polar covalent bond. Okay. So that is what here written. Non-polar when it is when there is exactly similar sharing of the electron between the two atoms. Okay. But in one, sometimes what happens, two dissimilar atoms are there. Definitely one of them is going to utilize the electron more and another element is going to utilize the electron less. That time more utilizing will get the more partial negative, less utilizing will get the uh, partial positive. Okay, so that is what polarity of the bond. I think it is clear now. Now let's see the next slide of the same topic. See, dipole moment. What is dipole moment? How much polarity is there? How much electron moved from the less electronegative to more electronegative? That is called as a dipole moment. Okay. See here, I will clearly explain. This is hydrogen. Okay. This is some halogen. It is supposed to be exactly at the center. Okay. But there will be more pull from this one because it is more electronegative. This will also try, but the trial is very less. So because of that, what happens after some time, okay, then electron will be more away from the hydrogen, more close to halogen. Okay. So now this will get which charge? Partial negative charge. And this will get which charge? Partial positive charge. Okay. So how many poles are generated? Two poles are generated. Why two poles? Movement of electrons. Electrons are moved from hydrogen towards the halogen. That's why this is called as a dipole movement. Okay. Now denoted with what? Mu, and it is formalized charge on the pole. That is, you can take either of the charge. Both will be exactly equal. But what will be the opposite? Sign will be opposite. This is plus, this is minus. And into the distance between the poles. That is distance between hydrogen and halogen. Okay. Now, these units are dBi. Actually, dBi is the scientist name. Every scientist want their name is to be taken again and again, so that even their soul must be rest in peace. Okay, so they will write the units as their name. Okay, so dBi is denoted with D. So 1 dBi is equal to 3.333564 into 10 to the power of minus 30. This is C means coulomb, M means meter. Okay, because we are talking about the charge. Okay, so one of our teacher studied it as a centimeter. No, it is not centimeter. It is coulomb meter. Okay, so C stands for coulomb, M stands for meter. This is for bigger people. This is following the system international. So if you want some local units, then CGS units, ESU centimeter. What are the units? ESU centimeter. 1 dBi is equal to 10 to the power of minus 8 ESU centimeter. And what do you call? Dipole moment is a vector quantity. We should be more worried who is taking the electron from whom it is taking. That's why it is denoted by the arrow. It is denoted by what? Arrow. Okay. So that arrow will represent, denoted by arrow. That arrow will be representing the direction of motion of electron. That arrow will be representing what? Direction of motion of electron. Suppose electrons are going in this direction. Okay. Electrons are going in which direction? In this direction. Then obviously there will be positive charge here and negative charge in this direction. So this is a representation of dipole moment diagrammatically. Okay. Suppose if I write HF, so electrons are moving, this is a bond. Electrons are moving towards the fluorine, due to which hydrogen will get the positive charge. That is what called as a dipole moment. What it is called as? Dipole moment. It is a vector quantity. Units are ESU centimeter, in local CGS units, and in standard system international it is, in standard system international it is what? It is coulomb meter. Okay, but in case of a, uh, but in case of a normal formula, charge into charge is on the any pole you can take, because both of them are okay, both of them are same. Okay, both of them have the same charge and distance will be different. Okay, so this is all about the dipole moment. This is all about what? Dipole moment. Okay, Now let's see the next. More questions are there. I have collected some cute, most repeated, most confusing questions, and it's all just for you cute people. Okay. So in a polyatomic molecules, the dipole moment not only depends on individual, but also depends on net dipole moment. Sometimes internally there will be dipole moment, but total value will be zero. Okay. So actually some students also do the same problem. Okay. They always work hard, but in examination they will do some damn thing and net result will be zero. Okay. So it is not that he has not done hard work. Same happens with the carbon dioxide also. Internally, if you cross check, see this is a carbon dioxide. Okay. So this is carbon dioxide. When you say dipole moment total, mu net you will get it as a zero. So you will feel that acha there is no dipole moment, there is everything is okay. But when you see go and inside and see, you will be surprised to see you will find four dipole moments. Okay, one dipole moment will be here, another dipole moment will be here, another dipole moment will be here, and another dipole moment will be here. But when I sum all of them, this is getting cancelled with this one, this is getting cancelled with this one. So net will be zero. Okay. So polyatomic molecule net dipole moment not only depends on individual dipole but also depends on the direction. Okay. That is called as a spatial arrangement. In such case, dipole moment of them, their net dipole moment, if you wanted to find out, there is a Ramban or there is a Brahmastra. That Brahmastra name itself formalizes this one. Okay. So here the resultant, R stands for resultant. This is one dipole moment, this is another dipole moment, and the angle between those two dipole moments. See, let us take this is one dipole moment. This is another dipole moment. Between them angle is what? Theta. But net if you calculate, you will get in this direction. The direction of net dipole moment is not zero because they are not cancelling. Here why they are cancelling? Because cos, what it is there? 180. Okay, the bond angle separation will be 180. So if you put here cos 180, the answer you will get as a 0. Okay, so that is what net dipole moment. Okay. Now let's see some cute questions and cute information, cute orders. Here, applications of dipole moment. Okay, there is a board question, so many times repeated question, board question, because in board exam, what they will see, copy and paste. Take 2 to 3 years back one question and paste it here. Take last year question, paste it here. Take 7 years back question, paste it here, and you will get a wonderful new paper. Okay. So the dipole moment is helpful in predicting the geometry of molecule. Question what they will say, H2O, CO2 both are triatomic, but H2O is bent structure, CO2 is linear structure. Explain with the help of the dipole moment. Okay. So then what you will write? In CO2, when the net dipole moment is determined, its net dipole moment found to be how much? Zero. But in H2O, due to bent structure, they are not able to cancel with each other. Okay. So while I am drawing, if you are a sincere student, you should get doubt, sir, why you are drawing this arrow towards oxygen, sir? Why you are drawing towards this like this, sir? How you will come to know? This arrow will point towards the more electronegative. Okay. Suppose if the same question comes like this, OF2, then dipole moment will be from dash to dash. Okay, we will say from dipole moment will be from which oxygen to fluorine, fluorine to oxygen, or can't say. Okay, now we have studied about this bond angle. If you are given with bond angle, you should be in a position to find out the dipole moment. This is the resultant dipole moment and it is the individual dipole moment. So this dipole moment will be given and this dipole moment will be given. And what is the net value? Net value will be in this direction. Okay, this is what I told you. Now let us take some examples, then it will be more clarified. Okay, so let's take applications of dipole moment. Okay, so here after finding out the dipole moment, what will be the uses? First use, dipole moment is helpful in predicting the geometry of a molecule. First of all, if you wanted to find out H2O is linear or bent, simply find out its mu net dipole moment. Okay, if it happened to be zero, that means it is linear, because if it is linear, then dipole moment will be towards the oxygen. Always dipole moment will be from less electronegative to more electronegative. So the net dipole moment will be zero here. Okay. So, but if it is not zero, that means it is not linear. So then what is the other option? Bend. Okay. So like that we can predict. The same thing was done. See, CO2 has zero dipole moment. Then it shows that it is linear. H2O has some net dipole moment. That means it is not linear. Therefore, it is bent. Okay. So first use is to find out the dipole structure of the molecule. Okay. Second example, second use, where the dipole moment is more, and this is most wrong answered question. Okay, most of the time it is wrong answered question, so you have to be very careful. People will feel that NF3 more electronegative, so more dipole moment, but it is not like that. Okay, why? Because there are dipole moment, individual dipole moments are more, that also I agree, but they are not in right direction. See, one wanted to go in this direction, another wanted to go in this direction, another wanted to go in this direction. So because of which the net dipole moment will be less, mu net will be less. Okay, you do any amount of efforts, but if it is not in the proper focused, see here, when you individually see here, the dipole moments are very, very small, but they are in the all are in one direction. Okay, so this is also wanted to go in this direction. This is wanted to go in this direction. This is also wanted to go in this direction. So that means everybody once wanted to go on in that direction. The net value will be always more. Okay, so the net value will be always more. That means you have to stay focused. Once you diverge your efforts, the result will be zero like this. Okay. So here again I am explaining in NH3, three forces are acting. In NH3, one force is acting in this direction, another force is acting in this direction. So these are the small forces but acting together. So once forces acts together, they will be added up. Okay, but in NF3, actually fluorine is more electronegative than nitrogen. Then dipole moment will be from nitrogen towards the fluorine. And here, why the dipole moment is from hydrogen to nitrogen? Because nitrogen is more electronegative. Always remember, dipole moment will be from less electronegative to more electronegative. Okay. See here, less electronegative is nitrogen, more electronegative is fluorine. So here, simple imagine if three people are pulling in the opposite direction an object, then movement will be less. But if the same people act in same direction, if all of them are pushing like this, then definitely this motion of this body will be more. Okay, so this is what happening in this one. That's why net dipole moment in NH3 more than net dipole moment in NF3. This is so many times asked and people are answering wrong. All will think that more dipole moment will be there in NF3 because fluorine is more electronegative. But it is a wrong assumption. Okay. In NF3, people are working in all different directions. If forces are acting, wonderful forces are acting. But if they are in opposite direction, what is the use? So that is what happening. I think now it is clear. Okay. So this is the order of dipole moment. Here also see all dipole moments are towards the nitrogen. If all in one direction, definitely it is going to give you good result. If all are in opposite direction, then See, opposite. Okay, resultant will be less. Okay, so always you also in the life also always work focused. All effort should be in one direction. Okay, so if you put the half work in other, half work in other, then you will not get anything in your life. Okay, so next to identify the isomers. Third use is, first of all, we have found the structure. Okay. Second, we found the direction of dipole moment. Okay. And third one to find out the isomers. Okay. So these are the two isomers. This is called as a cis and this is called as a trans. What do you mean by trans? See here, chlorine, one chlorine is in this direction and another chlorine is in the opposite direction. Okay. Trans means opposite, cis means same side. See, this chlorine and this chlorine, both are in the same side of the double bond. And here hydrogen and hydrogen, both are in the same direction. Same means cis. So here, as a shortcut, cis contains same. Okay. So cis same. Like this, you can understand. So if the same groups are on the same side of the double bond, then it is cis. And in this one, all dipole moments are acting in one direction. See, this is the direction, this is the direction. Okay. So it can never be zero. But here, one dipole moment wanted to come in this direction, another moment want to come in this direction. Like this. Okay. So therefore, both are equal only. Both are the dipole moment between carbon and chlorine, carbon and chlorine. So resultant dipole moment will be what? Zero. Okay. So if you pull an object with equal force but in opposite direction, then the displacement will be zero. Same thing is happening here. This is pulling this side, this is pulling this side. So resultant will be zero. So if you are in doubt that our molecule, like this molecule formula will be C2H2Cl2. You are given with only this molecular formula, but you don't know that whether it is cis or trans. Then find out its net dipole moment. If its net dipole moment is zero, that means you can say it is trans. If it is not zero, that means you can say it as a cis. This is the third application. Next, fourth application will be again position isomers to find out the position isomers. Okay. So in benzene, in mono substituted benzene, which substituted benzene? In mono substituted. That means let us take only this chlorine is substituted. Okay. So this position is called as a ortho. This position is called as a meta. This position is called as a para. This position is called as a meta. This position is called as a ortho. So like that, whether the second chlorine is substituted at ortho or meta or para. For that also we will calculate the dipole moment. If it is zero, then definitely it will be para, because again same criteria. One force is acting in the top, same force is acting at the bottom also, but in the opposite direction. So if your dipole moment is zero, then position isomer will be para substituted. What it is? Para substituted. And in case of the meta, see, this is the meta. It is in the 120 degree. Okay. So like this question will be coming. So you will be getting mu1 plus mu2 plus that formula mu1 mu2 into cos 120, because total it is 360 degree, and here the bond angle total it will be divided into how many equal parts? Three equal parts. So bond angle you have to take it as a 120. If like this, it will be 60, 60, 60, 60, 6 times it will be 360. And here bond angle will be how much? Very good. It is 60 degree. Here 60, here 120, here 180. As the angle of separation between two vector increases, the resultant energy, the resultant dipole moment will be decreasing, and it reaches minimum to the zero in the para. Okay. So like this, you can identify whether our dye substituted is ortho, meta or para, and some wrong impressions. So like I told you, NH3 and NF3 question, most of the student got negative marks, and same negative marks got in the this one also. Okay. So people will think that Acha sir told that para will be always 0. Okay, I agree, but only this one, but not this one. Why? Because here this carbon is sp3 hybridized. In sp3 hybridized, it will be three-dimensional structure. So this will lie in this direction, let us take, and this may lie in this direction. So, but here C triple bond N. So triple bond N will be linear. For the time being, if you don't know hybridization, wait for that. Then I will tell you why it is linear. Okay, why it is sp hybridization. Then you will come to know about this. For the time being, what you will take, see, this is in this direction. Now all are acting in the one direction and opposite. Therefore, answer will be 0. But here it is not like that. The force is going like this. The force is going like this. So it is not cancelled properly. Same problem with the SH also. Here this hydrogen may be this side. Here this hydrogen may be this side. So it will not be get cancelled. This will get cancelled only all are in line. All are in line. So non-planar, non-planar. But it is planar. Therefore it will be 0. So never think that para will always be 0. Mostly it will be 0, but not always 0. Okay. Now let us take this structure. This is chloromethane. This is dichloromethane. This is chloroform. This is CTC. CTC means CTC plaza. It is not. It is carbon tetrachloride. Okay. Now in this one, see carbon tetrachloride. So here all are carbon and chlorine bonds only. So everything will get cancelled and its mu net will be 0. Okay. But if it is substituted hydrogen, okay, now the dipole moment will be only acting in the bottom direction. Therefore, it decreased. And one more, if I replace with hydrogen, this will also not be there. And highest dipole moment will be there when only one place it is chlorine, rest all places are hydrogen, because all will be directing in one direction. Okay. Here, this is, let us take structure. So here carbon and chlorine, and this chlorine, carbon to chlorine, okay, hydrogen, hydrogen and hydrogen. So all are moving in one direction. So definitely the movement will be maximum. Okay. Here it is not like that. Coming in one direction and going in two direction. Two chlorine are there. Coming in one direction but going three direction. And now all are going in the opposite direction. So this will be 0. Same way mu CH4 also 0. Whenever you find all elements of same type, then net dipole moment will be 0. Okay. So this is about the dipole moment and misconcept. Misconcept is about this one, and in the previous I told you about the NF3 and NH3 question. Okay, so you should not get negative because already you understood the problem. Okay, so learn mistake from the others. Then hybridization also you can determine. Okay, so suppose if it is a linear, that means there is no lone pair. So there is no lone pair means linear means only how many bonds are there? Two bonds are there. So two bonds means hybridization will be sp. Okay, because only two bonds are there, so two orbitals are required. That's why I have taken sp only. Here again three bonds are there and dipole moment is 0. So 3 means I have to take 3 sp2. Okay, so sp p2 and s1. That's why the dipole moment, when if it is 0 for the molecule of AB3 type. Which type? AB3 type, like BCl3, BF3, then dipole moment will be how much? It is going to be 0. So this is the next application. Okay. So slowly you should note down. Understood? Afterwards also you can note down by taking the screenshot. Okay. Then dipole moment directly proportional to electronegativity difference, not electronegativity. See here, hydrogen is same in all. Then more electronegative we will take fluorine, therefore dipole moment will be there. Understood? Second thing, dipole moment proper, these are the characteristics on which dipole moment depends. First is electronegativity, directly proportional. Second, dipole moment directly proportional to number of lone pair. Okay. So here in fluorine, how many lone pairs will be there? Three lone pair. Why? Because fluorine atomic number is 9. So 1s2, 2s2. Okay. 2s2 and 2p5. So then it will be 9. Okay, 9 electrons are there. Now out of this 2p5, I am drawing it here. Out of this 2p5, 2s2 is also there and 2p5 is also there. So 2s2, okay, and 2p5. So 2p5. Uh, okay, this is the unpaired electron. So this is forming the bond where in CCl5, sorry, in HF, okay? In HF, fluorine is forming one bond. So how many lone pair are there? 1, 2, and 3. So this is having 3 lone pair. And oxygen will have 2 lone pair. Nitrogen will have 1 lone pair. So according to here, more number of lone pair, more number of lone pair, more will be dipole moment. So highest dipole moment is found in the HF, less dipole moment found in the NH3. What is the reason? Lone pair are less in NH3 and lone pairs are more in HF. Okay. Then for atomic molecule and molecules having normal shapes such as linear, trigonal and tetrahedral, okay, possess zero dipole moment. Okay. So let us take CO2. So in CO2, it is not that it don't have any dipole moment. It have, but both are equal and opposite. Therefore, net dipole moment will be how much? It will be 0. Okay. And N2 are non-polar, O2 are non-polar, Cl2 also non-polar. So they do not require any dipole moment. Suppose if they have distorted shape. What is distorted shape? Let us take the H2O. In H2O, oxygen is sp3 hybridized. So sp3 hybridized, it should be what? According to hybridization, sp2, sp3 like that. According to that, it is supposed to have tetrahedral shape. What shape? Tetrahedral shape. But the problem is that it is having bent shape. This is called as a irregular shape. Okay. So then they will definitely have the dipole moment. If it is tetrahedral, then there is no dipole moment. But it is having distorted shape. Why? Because of the lone pair. Why it has happened? It is because of the lone pair. Understood? Okay, very important questions. The on this numericals will be coming. Okay, ionic character in a covalent bond. This already it is there in the periodic table. Okay, this topic you will get in the periodic table also. But problem, what is the problem? Problem is that their formula is different. In periodic table, we will calculate the percentage ionic character by using the electronegativity scales. Electronegativity scales. Okay. So in the NCRT also it is mentioned electronegativity scales are Pauling scale. Okay. And Aldred-Rashko scale. Pauling scale is mostly used, but we are not using that now. We are using the dipole moment, percentage ionic character, percentage covalent character. We can find out, we can compare by using which law? Suppose we don't want value, we want only where ionic character is more, where covalent character is more. Which law you will use? Okay, in the periodic table, it is based upon the electronegativity scale, and here it will be based upon the dipole moment. Okay, so there are two types of dipole moment. By sitting and using the calculation, we can calculate. Okay, and by doing and calculating, this is the observed dipole moment. There is a lot of difference. Okay. So some people will say, I can do that, I can do this. But when they are asked to do, then they cannot do anything. Therefore, their efficiency is what? Zero. Okay. So I used to do like that, and all these are all calculated. But when they are practically doing, that is called as observed. Okay. So that ratio is called as a percentage ionic character. Okay. Now let us take H and Cl for example. So in that what we will take calculated, it will be dipole moment is equal to Q into D. So distance will be depending on the sum of the hydrogen and chlorine atomic radius, or you will be given with distance. That you will put it here, and this value either they will give you. Okay. So after substituting here, then into 100. Okay. So you are supposed to suppose you are given with 3. Okay, 3 dipole moment from calculated. But when you exactly calculate, you are getting only 1.5. So that means percentage ionic character is 50% and percentage covalent character will be 50%. Like that, you will be calculating the percentage ionic character. Okay. So next theory after dipole moment, next theory is valence bond theory. Which theory? Valence bond theory. It was proposed by Hitler and London. Okay. London is also not city name, it is a person name. Okay. So Newland also person name, London also person name. Sometimes person name matches with the place name also. Okay. So here, valence bond theory is proposed by Hitler. Yes, okay, Hitler and London to explain what shapes of the covalent molecule and their bond angles and bond length. Everything was explained. So valence bond theory and molecular orbital theory. MO means molecular orbital theory. They based upon the quantum mechanical model, that is atomic structure we have used, and was extended by the starting was done by the Hitler and London, but further it is explained by the Pauling and Slater. Okay, Slater will explain the directional nature of the covalent bond. Okay, so in this there is not much to remember, it is just introduction. Now actual topic will be there. So postulates, what are these? These are the postulates. Okay. The first postulate says that covalent bond is formed by, first postulate says that covalent bond is formed by overlapping of the orbital having unpaired electron. Okay. So now I will tell you one simple and logical, easy understanding question. Suppose this is the hybrid or atomic orbital. Okay. Now how many electron can participate in bond formation? Question is how many orbital can participate in bond formation? Okay. Okay, here two unpaired electrons are there. So overlapping of this orbital, and this is S, this is Px, this is Py, and this is Pz. So according to this theory, only Py and Pz can form the bond by the overlapping. Okay. So dative bond is also formed by overlapping of orbital having pair of electron with vacant orbital. So this will form the covalent bond. Okay. What it will do, this will have the covalent bond. And dative bond, this is ready to form dative bond. Okay. So what is dative? Simply the things will be of the S, but it will be appearing to be used by the other atom. Okay. So like NH3. In NH3, this lone pair dative bond will be by the nitrogen. Let us take towards the H plus. So this total authority over the lone pair will be from NH3 only, but utilization it is done by the hydrogen. Okay. So this is what the dative bond is. Understood? Now simple logic: unpaired electrons covalent bond, lone pair electrons coordinate covalent bond. Coordinate covalent is also called as a dative bond. So now it can form total how many bonds? 4 bonds. But out of those 4 bonds, Two bonds must be covalent. Okay, two bonds are covalent, two are the dative bonds. What is the difference between the dative bond and covalent bond? Okay, so in dative bond, one will be lone pair, another will have empty orbital. In covalent bond, both will have one electron each. Okay, so let's see the next one. Then greater the extent of overlapping, greater will be the strength of the bond. So it is about the overlapping. Okay. So suppose in P and P, this is P orbital. Okay. And this overlapping is called as a axial overlapping or head-on overlap. So let us take this is P and there is one more P here. So the joining area is up to here. Understood? So the large overlapping area, therefore large chemical bond. Understood? So less overlapping area. Let us take the overlapping of s orbital with s orbital with p orbital. Let us take. So overlap area is reduced or not, and less overlap area will be there further in S and S. So that's why overlap area decreased, so bond energy decreases. Overlap area increases, bond energy also increases. Okay. If two atoms are approaching each other having nuclear Na and B, then they are represented by Ea and Eb, electron of A and electron of B. Okay. Anyhow, this series is sufficient. P dash P greater than S dash P greater than P S dash S. This is on the basis of overlapping area. On the basis of what? Overlapping area. Now let's see the next one. Next postulate. So covalent bond is formed when electron cloud concentrated on in the internuclear axis having cylindrical symmetry called as a sigma bond. What does it mean? Suppose this is one carbon, this is another carbon. So the electron cloud must be between both carbon atoms. Between both carbon atoms. So this is sigma bond. Okay, this is cylindrical and this is the carbon atomic bond, that is also carbon atomic bond. Okay, so between them direct overlapping is there, that's why it is called as a sigma bond or linear overlapping of atomic orbital. This linear is also sometimes called as a head-on, which on head-on overlap of atomic orbital. Okay, then a covalent bond formed by sideways overlap. Sideways means one p orbital is like this, another p orbital is like this. Okay, so if they overlap like this, then it will be pi bond. If they overlap like this, then it will be sigma bond. Okay, so atomic orbitals already, but pi bond cannot take place single. This is very important. Covalent formed by the sideways overlap of atomic orbitals already bonded through the sigma bond. Without sigma, you cannot imagine pi bond. First, if you ask, will you form pi bond? Then it will ask, already sigma bond is over. Then I will come and form the pi bond. Understood? Because for pi bond, they should be very closer. So when they will be closer, when there is already sigma bond is between them. Okay? So there is no existence of single pi bond. Always first will be sigma bond, then it will be pi bond. Is it clear? So lateral overlapping of atomic orbital results in pi bond. Pi bond is only after formation sigma. Any type of orbital. Okay. So any type of orbital can involve sigma bond formation. Sigma can be formed between S comma S. Sigma can be formed between S comma P. Sigma can be between P comma P. P comma D. Everybody can do the sigma bonding. But pi bond is not like that because S sub shall have no side. Everything is front only, but because it is spherically symmetrical. So there is no sidewise thing in the S orbital. Therefore, S orbital can never and ever form the pi bond. Okay, it can only eligible for sigma bond. So who are forming P and D orbital can form pi bond. One single bond is equal to sigma bond. Suppose A and B are forming sigma bond, single bond, then it will be sigma bond. But the next bond will be A and B, second bond will be pi bond. This is about the sigma and pi bonds. That is valency bond theory main postulates. Okay. Okay, after this, the next slide is about double bond is a combination of one sigma bond and one pi bond. Okay. Once we say that double bond is there, that means there among that first formed bond will be sigma bond. And that after that, whatever the addition is there, there can be only pi bond. Okay. There is no two sigma bonds are possible. No two sigma bonds are possible between any two atoms. Okay. Then triple bond is a combination of one sigma bond, one sigma bond. Pi bond can be any number, and that to maximum two are possible between any two atoms. Between any two atoms. Okay. Between any two atoms, there cannot be more than one sigma bond, and cannot be more than two pi bonds. Cannot be more than two pi bonds. Okay. So always sigma bond is greater than pi bond because it is overlap. Area of overlap is very much high. Okay. Area of overlap. Area of overlap is high. That's why this is possible. And sigma between two p orbital area is more, and between S and P is further less and least is pi bond. Okay. So X sigma bond between 1s and 1s. 1s and 1s is the exceptional. Actually, it is supposed to be weaker, but between 1s and 1s, it is exceptionally stronger. Okay. It is supposed to be weaker, but it is stronger. Okay. So let's see the next slide. So strength of the bond as follows. Triple bond always greater than double bond greater than single bond. And pi electron is, sigma electron is localized. Localized means suppose here between the A and B electrons are there. They will stay there itself. It will not go anywhere else. But pi bond electrons are there. Then what they can move here, they can move here likewise. They are mobile electron. Why? Because this is weak. Okay. Pi bond is what? Weak. So because of the weak pi bond, it can break anytime and it can move from one place to another place or within the molecule. Okay. So next, shape of molecule are determined by the sigma bonds and pi bonds. Okay, do not affect the shape of molecule. So if it is 3 sigma bond, let it be any number of pi bond. Pi bond will not decide the shape. Only sigma bond will decide the shape. The reactivity of multiple bond is always more than a single bond. Suppose there are triple bond is there, always it will try to break this pi bond. That's why it will be always more reactive than the single bond. Okay, because pi bond is weaker, so nobody want to keep the weak bond with itself. Okay, when orbitals of two atoms come close to form a bond, then the overlap may be positive, negative, or zero overlap depending on the sign and direction of orientation. What is that? That we will see here. Okay. So there are three types of overlap: positive overlap, negative overlap, and zero overlap. That means overlap is not at all taking place. Okay. So this is what the zero overlap. See, this is zero overlap. Actually, here this is s orbital. What is this? This is s orbital. Okay. So s orbital cannot form. S orbital cannot form sigma bond with p orbital. It can only form. It cannot form. See, their overlap area is almost zero. Okay. So very less negligible. That's why this is called as a zero overlap. Okay. And here, what is the problem? This is z axis. This is on the y axis. This is on parallel like this. I will tell you like this. Okay, this is the direction of this. This is the direction of this. Okay. So because of this, overlap is not possible. These are the some examples of zero overlap. Okay, between px and py there is no pi bond, there is no sigma bond. Between s and s orbital and p orbital there is no bond between them. The pi bond is not there. Sigma bond is possible. Like this it is possible. Okay, so pi bond is not possible between p pi and s pi, will not be possible. Even s pi also not possible. Okay, so this is about the zero overlap and very important. Already one exam in exam, which of the following overlaps are possible. Okay, so now let's see the next one. This up to here we have studied about the valency bond theory. Valency bond theory, VB theory. Now we are going to study with the VSEPR theory. VSEPR theory is valency shell electron pair repulsion. Okay. V stands for valency, S stands for shell, E stands for electron, P stands for pair, R stands for repulsion theory. Okay. Actually, it was originally given by Sidgwick and Powell. These are the two scientists, but it is further modified and made attractive by the Neilholm and Gillespie. Okay, so VSEPR theory, according to them, the shape of molecule depends on number of electron pairs in the valency shell. Okay, the electron pairs are divided into how many types? Bonded, or it is also called as shared pair. Non-bonded, it is also called as a lone pair on the central atom. Okay, if the central atom is surrounded only by the bond pair, then molecule is supposed to be regular shape. What is regular shape and irregular shape, that we will come to know when you go for the hybridization. Lone pair is there, irregular. Lone pair not there, then it will be regular shape. Simple as of now, you can remember that. Let's go for the next one. The pair of electron in the valency shell, the pair of electron in the valency shell repel one another since their electrons are negatively charged. That means always there will be repulsion only between the electron pair. Let it be lone pair, let it be bond pair. Always they repel each other. You can never find two electrons sitting together and chit chatting, because they are enemies with each other. They never talk to with each of them. Okay, these pairs of electrons tend to occupy such position in the space that minimize the repulsion. Okay, so always they will try to separate largest possible separation. They will try to make so maximum separation so that minimum repulsion. Okay, a lone pair of electron takes up more space than the bond pair of electron, because lone pair is under the control of only one atom. Bond pair is under control of two atoms. Okay, suppose A and B are forming the bond, then this is attracted by this atom also, this is attracted by this atom also. So because of that, their two nuclei will press them, will utilize them so nicely that there is no freedom. Understood? But if it is of lone pair, then in lone pair there are chances. It is only by the one atom only. Okay, therefore the space it is rotated or available will be more. Understood? Then the repulsion between electron pairs is follows lone pair greater than lone pair bond pair greater than bond pair. So for this I will write an example here itself. Oxygen. Okay, so this is hydrogen, and this is lone pair, and this is lone pair. Okay, so now I will mark with the different color. Okay, so this repulsion will be of lone pair, lone pair. It is of lone pair. Okay, and next I will pick which color. I will pick purple color. Yes, purple color. So this color, this repulsion is of lone pair, bond pair. Okay, then now I will pick green color. Okay, this repulsion is of bond pair repulsion. Okay, so all the varieties you found in the water only. Now, after if you understand My question is, my question is, I am using another color so that you should not get hint. This repulsion is called as, this repulsion is called as, okay. So can you identify? If you understand my previous example, then you can answer. Okay, so this will be of the lone pair, bond pair repulsion. Understood? So in water molecule, there are one lone pair repulsion, one lone pair, bond pair repulsion, sorry, two lone pair, bond pair repulsion, one bond pair repulsion. Okay, so this is about the types of lone pair and bond pairs. Is that clear? Now let's see the next one. So these are the lone pairs and bond pair history. Okay. This is complete history of lone pair and bond pairs. Okay. Number of bond pair, number of lone pair. Here, if it is two bond pairs are there, okay, and no lone pairs are there, then it will assume which color? Then it will go for the linear shape. For example, BeCl2. Okay, I am drawing it here. In BeCl2, the bond angle will be 180 and shape will be linear shape. Same way BeF2, C2H2. Okay, C double bond. Sorry, H and C triple bond, C single bond H. So like this, this is a linear shape. Then AB3 triangular planar. Here boron with the 3 fluorine, but when you combine them, when you join them, you will get a triangular shape. This will happen when 3 lone pair and 0 bond pairs are there. Sorry, 3 bond pairs and 0 lone pair. If 4 bond pair, 0 lone pair are there, tetrahedral. So this is the shape of a tetrahedral. Okay, so likewise you can find all structures T shape, bent, and this you have to remember, and I am writing it here. B is outer atom, okay, outer element, and A is central element. A is central element, and wherever you find E means it will be lone pair. So that means here two bond pairs and one lone pair. So that time instead of it is linear, it will be bent shape. One part will be, suppose this is a lone pair and this is a bond pair. Like this it will be there. Understood? So now I think it is clear. So this tabular form, try to write it with your own words and then you can practice them. Okay? Practice only the way you can understand this much better way. Okay? Now next, let us talk about the hybridization. Okay. Okay, our next topic is hybridization. First of all, what is hybridization and who introduced? Pauling introduced the hybridization. Okay. Pauling is the scientist who introduced the hybridization. And what is hybridization? Intermixing of atomic orbitals of almost same energy and their redistribution into equal number of identical orbitals known as hybridization. Okay, so actually suppose here it is written the orbitals of one and the same atom only involved in hybridization. Let us take PCl3. So all atomic orbitals of P only will take part. Okay, or PCl5, anything you can take. Central atom will undergo hybridization. Okay, in hybridization, what happens? Suppose these are the orbitals. They are having nearly same energy. Okay, somewhat larger, somewhat less is okay. Exactly same energy will never be there. But suppose this is exactly different, so it will not participate in hybridization. These four will participate in hybridization. Okay, so they all mix with each other and will form four are mixed, four orbital will be formed, and all the four orbital will have the identical same energy. Okay, so this is what here written. Molecule of the central atom only will undergo hybridization. Orbitals formed in hybridization process are called hybrid orbital. So before hybridization we will have atomic orbital. After hybridization we will have the hybrid orbital. Okay. So number of hybrid orbital produced is exactly equal to number of atomic orbital combined. Okay. This is about the concept of hybridization. Now let's see the next one. Okay. So here atomic orbital, what they are mixing and what it will be formed. Suppose from an atom, one s orbital combined with one p orbital, 1 and 1, so sp, and hybridization, then the shape will be linear shape. For example, BeF2. Okay. Same way, one s orbital, two p orbital, sp2 hybridization, triangular planar, one s orbital, 3p. This number represents number of orbital. Okay, then it is CH4. Example, tetrahedral. One s orbital, three p orbital, and now d also added up. So d1, nothing is written means 1. So TBP, in the exam they will write short form TBP, trigonal bipyramidal. So that time hybridization will be sp3d and shape trigonal bipyramidal. Examples are PF5 and PCl5. One or two examples I will tell you. Okay. So S1s 3p and 2d, sp3d to octahedral, 1s 3p and 3d, then pentagonal bipyramidal, 1s 1d 2p, dsp2. This rarely you will find square planar shape. Okay. So now we will do some examples on the whiteboard. Okay. So let us take how to identify the hybridization, how to decide the shape. Suppose let us take a simple example of boron trifluoride. Okay. So this is where you have to identify the hybridization. Here central atom you will take. Central atom is what? Boron. And its atomic number is 5. 1s2, 2s2, 2p1 is the electronic configuration. Okay. So these are the 2 electron and this is 1 electron. In the valency bond theory already we have studied only unpaired electron can form a bond. But here how many unpaired electrons are there? Only one unpaired electron is there. But we want how many unpaired electrons? 3 unpaired electrons. So this is called as a GSEC, ground state electronic configuration. Now this electron will transfer here so that number of unpaired can be increased to 2s1 and 2p2. Okay, 2s1 and 2p2, 2s1 and 2p2. Now how many unpaired are there? 3 unpaired. So our requirement should be fulfilled anyhow. Understood? So the hybridization will be from here to here. Okay. So then it will be sp2 hybridization because one s orbital, two p orbital. Understood? All are single electron. Therefore, it will be 3 bond pair. Okay. Now, once it is sp2 hybridization and 3 bond pair. Now, let's see what is the shape and how we should write. Okay. So, in this one, we will refer according to table what it is given. Okay. See here sp2. Here it is mentioned, I think. Now it is clear. Is it visible to you? Okay. So here this is sp2 hybridization. What should be the shape? Triangular planar. Now we will draw the triangular planar. Okay. What we will do? We will draw the triangular planar and you will come to know how it appears. Okay. So sp2 hybridization. So at the center of a triangle, it will be boron. And all the 3 corners of a equilateral triangle is occupied by the fluorine, 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 and fluorine. Okay. So here in simple, the bond angle will be how much? It will be 120 degree. Okay. So this is how you will find out the hybridization. Understood? Now hybridization is very easy or not? Yes. Okay. The more you practice, the more better you will feel and more confident you will feel, and it is useful in the entire inorganic. Inorganic without chemical bonding you cannot imagine. Okay. So these are the some shapes are given and you can uh, practice them. Okay. And in the practice session. Now let us see some theory questions from the hybridization. Okay. First, the hybrid orbital involve only sigma bond, do not involve pi bond. Suppose carbon, it is triple bond and single bond. So only this sigma bond will participate in hybridization. This will not involve, this will not involve. Okay. Next, hybrid orbitals are more effective forming stronger band that leads to the formation of more stable molecule. Without hybridization, if they make, then it is very unstable. So that's why they will go for the hybridization before going for molecule formation. Like Amitabh Bachchan says in ad, so before you paint or before you make some wall, you have to mix something to leak proof, to make the walls leak proof. So like that, to improve the stability before formation of molecule, you have to hybridize them. Hybridization before the hybridization before the molecular formation will improve its stability. Okay. Yes, Dr. Fixit. Okay. So when you add Dr. Fixit to your cement, I think, so that will avoid the leakage. It will improve the lifetime of your entire house. Same way, before formation of molecule, if atomic orbitals undergoes hybridization, that leads to more stability. Okay. Then same atom can undergo different types of hybridization under different condition. Okay. Suppose carbon is there and it is not that lifelong, it will not, it will go sp3 hybridization only. Situation changes, it will also change. You have to change according to the situation. Okay. It can participate, it can go for sp hybridization also, sp2 also, sp3 also, because you don't know how many customers will come. Suppose one day one only two customers came. Okay, so that then that time what it will form only is two sigma bonds. So that time hybridization will be what? sp hybridization. And one fine day, four customers came. So then it will form how many sigma bonds? Four sigma bond. Then that day it will go for the sp3. So it is not that carbon sp3. You will just by heart like that. Carbon can be sp3, carbon can be sp2, carbon can be sp. That depends on what customers. Okay. So, but we don't write it in the exam as a customers. We will write it as a situation. Understood? So more directional bond, greater is the bond strength. Okay. See, more directional means sp3, sp2, sp, p and b, unhybrid, unstable, unhybrid, unstable, unhybrid, unstable, more hybrid, more stable. Okay. So this is about the hybridization and its implications. Now let's see the shortcut formula. Okay. Instead of every time you write that procedure I told you, you can write it as a shortcut. Okay. Put in this formula, get the answer. Okay. So what is this shortcut? S plus half into G minus V, A minus C. Okay. But what is S? And better than this shortcut also I will tell you, no formulas, direct. Like Sunny Deol says, Sunny Deol I think, no if, no but, only JAT, or no FR, only final solution, no code. Like that, no formula, no substitution. Okay. But you will find this formula in many books. That's why I have to tell you. Okay. S is number of shared electron. G is group number or valency of electron. V is the valency of central atom. C is the charge on cation. A is the charge on anion. These many things. Now the total answer you will select here. If it is EP, that is electron pair. If answer is 2, then hybridization will be 2. Sorry, SP. If answer is 5, then hybridization will be SP3D. Okay. So now I will tell you my procedure. No formulas, no substitution, no simplification. Direct answer. Okay. So let's take, for example, if the question is, now you have to tell for hybridization of BrF3. Okay, it is not boron, it is bromine trifluoride. Understood? So bromine will contain how many electrons? 7 electrons. Out of that, how many bonds are made? 3 bonds are made. So how many electrons are left? 4 electrons left. Okay. So these are the 3 bonds. What are these? These are the 3 bonds. 4 left. With 4 left, how many pairs you can make? 2 pairs you can make. 2 lone pair. Simple. 3 plus 2 is equal to 5. So for 5 you have to write as P3, total 4 only you want 5, you write sp3d. That's all. Okay. So for sp3d hybridization, what will be the shape? Triangular and bipyramidal. Triangular and bipyramidal. This is triangle and this is bipyramid. Okay. So here, what I will write? Bromine. Okay. Bromine. And what? How many two lone pairs are there? Lone pair are the worst people in the world. They always repel with each other. So they are to be kept at as far as possible. So this is the maximum bond angle. Here it is 120 degree. That's why always try to keep the lone pair at the triangle so that they are separate, then they will be less janjat. Okay. So if I place here, then see 90 degree. That's why I should not place them here. Okay. Now BrF3, fluorine, fluorine and fluorine. Okay. So as a chemistry student, you should look it like this. Bromine, fluorine and fluorine and fluorine. Then your brother or sister who is in LKG, what they will say? It is T. What they will say? They will study it as it is T. So therefore the shape is called as a T shape. Like this you can immediately find out hybridization and everything fatafat. Okay. So this is about the hybridization shortcut formula. Now let's go for the next slide. Okay, so this is a shortcut than the shortcut. Shortcut to shortcut. Okay. Now let's see the next slide. Okay, now we have studied all the two bonds. What are the two bonds? Ionic bond we have studied, covalent bond we have studied. Now it's time for starting something new in the life, that is coordinate covalent bond. Okay. So coordinate covalent bond is also called as, in the somewhere I told you, I think I remember, but you may not remember. So dative bond, it is also called as what? Dative. Okay. Dative bond or coordinate covalent bond. The bond formed between two atoms by the sharing of electron pair. But this word is more related to covalent bond. Okay. But afterward, this word is necessary. Contributed by only one of the two atoms is known as coordinate covalent bond. Okay. Suppose by mistake you are you are cleared the IIT and you cleared the advanced exam also and you became IITian, and one fine day you got job in Infosys also. Okay. So Infosys you got job, and one fine day you went to office, but when you go to the office you found that you got only roti in your box. Okay. And same thing happened with your colleague also. He also joined in Infosys, and he also, on opening his tiffin box, he found only curry. Okay. Then both of you will sit together. You will offer him roti and he will offer you curry. Both of you will have lunch. So that the bond between you, that bond is covalent bond. Okay. So on other fine day, you got roti and curry, two boxes. Okay. By mistake, your kid box also kept into your box, and your colleague wife forgot everything. Then what you will do? You will offer both roti and curry, sit together and take that. That time the bond between you and him will be coordinate covalent bond. Okay. Both days you are sharing. but contribution is from only one atom, then it is called as a coordinate covalent bond. Okay. So coordinate covalent bond sharing will be done like covalent bond, but contribution will be from one atom. If both are contributing, then only covalent bond. If only one contributing, both are using, then it is called coordinate covalent bond. Okay. So then coordinate covalent bond is also known as dative bond or semi-polar bond or donor acceptor bond. Okay, because there will be some goodwill on that day I have taken your breakfast or lunch. So that goodwill will be there. You are the donor of my lunch. Okay. That day I accepted your lunch. That goodwill will be there. Understood? So coordinate covalent bond was proposed by the Sidgwick and name of dative bond is given by the Langmuir. Okay. See, job is done by somebody and name is given by somebody. Okay. So coordinate covalent bond is represented by arrow, and don't misinterpret this arrow with the if like this it is there. It is not coordinate covalent bond. It is called as so small changes. Here it is dipole moment. Okay. Here it is dative bond. Without plus dative bond, with plus it is dipole moment. So don't get confused with them. Okay. And here what it represents, this side you will find the donor, this side you will find the acceptor. Okay, the arrow whose it is pointed out, that points out the acceptor. The from origin of the arrow will be representing the donor. Okay, so for all practical purpose, coordinate covalent is treated as a single covalent bond. There was a very problematic situation about this word. Okay, so what happened and what went actually, that I am going to reveal you today, but don't tell it to anybody. This is a top secret matter. See, the formation of coordinate covalent bond, okay, occurs only after the formation of covalent bond. Okay, so you can never find the direct coordinate covalent bond. Okay, you will always find once covalent bond is formed and then extra is there. Okay, so extra electrons are there, then only it is going to form coordinate covalent bond, additive bond. Okay, so without suppose you are donating to somebody, when you will donate, after you are having sufficient. Understood? So this donor bond is always after covalent bond only. Okay. Now examples, coordinate covalent bond is present in N2O, ozone, N2O4, N2O5, CO. These are the neutral molecule example I am taking. And B3N3H6 is very famous nowadays. This is called as a inorganic benzene. What it is called as? Inorganic benzene. Okay. Now Al2Cl6 dimer of the AlCl3. When 2 moles of AlCl3 combine together, it will form AlCl3. Even hydronium ion, ammonium ion, nitrate ion, boron tetrafluoride, okay, fluoride, sorry. These are having coordinate covalent bond. Okay, that is very common. And see here, once I write square bracket, there has to be coordinate covalent bond. Actually here, this positive charge is of the aluminium. Now this lone pair on oxygen is donated to aluminium. Okay, contains 6 dative bond. Here 4 lone pairs are donated, 4 dative bonds. 4 lone pairs are there, 4 dative bonds. 6 lone pairs are there, 6 dative bonds. Okay. They are called as a complex, coordinate complexes, because they not only have coordinate bond, they also have covalent bond, sometimes ionic bond also. Okay, this is what I wanted to tell you earlier. Octet of the central atom, there is a practice of writing dative bonds in the structures of. Okay, so what is that? That I will tell you in the whiteboard. Okay, SO2. So in SO2, what they are doing earlier, or SO3 I will take, that will be best one. Okay. SO2 also okay, but first let me explain through the SO3. Okay, SO3, if it is earlier, it used to be like this. Okay, now sulfur is having 6 electrons, and once it shares the 6 electron with the 3 oxygen atom, and when you count all electrons, see total number of electrons on the sulfur is how many now? Tell me how many sulfur electrons are there? Okay, see, when I draw the sulfur trioxide structure as per the old pattern, okay, as per the covalent bond only, then it is having 12 electrons. It is having how many electrons? 12 electrons. See, 6 electrons it is having, and 2 is shared with each oxygen. So 12 electrons. Then people started asking, you are saying octet is best one, then why sulfur is making all this nonsense? Then they explained with the coordinate covalent bond. They told like this, okay? See, sulfur is having 6 electrons, and one day it shared only 2 electron with the 1 oxygen, okay? So this is the octet formed. Now it is peaceful. But another one day what happened? Another oxygen came. It said I have only 6 electron, but I want one more electron, two more electron. But if start sharing, then it will be problem with that. Then it donated this. Okay. So because of donation, there is no use of the electron of oxygen like this. Same way it happens with one more oxygen. Okay. So oxygen will not provide any electron. Now you count in the sulfur 1, 2, 3, 4, 5, 6, 7, 8. So now octet is there. That's why this dative bond is proved. Okay. Why dative bond is used is it understood to explain the extra stability which were considered as a superoctet. They were considered as what? Superoctet. There are 3 types of exceptions in the octet principle. Okay. If they are less than 8, then it is electron deficient. More than 8, superoctet or expanded octet. Okay, this comes under the expanded octet. Then they showed no, it is not expanded octet. There will be, now they are started writing like this: sulfur with coordinate, sulfur with coordinate, sulfur with double bond. Now you count, there will be always 8 electrons only. Okay. So now the NTA people got interest in this one. They started asking in integer type. Which type? Integer type. Number of coordinate covalent bonds and pi bonds, sigma bonds in SO3. So the answer will be coordinate will be 2, 1 sigma bond, 1 pi bond. So this will be the answer. Okay. So let them ask anybody. Once you are my student, it is my duty to inform you the latest trend of the questions. Okay. So now let's go back to the our topic. Okay. So this is what they said. Okay. This is very top secret. Don't reveal it to anybody. Okay. Let it be close friends also, don't reveal. Like that you can try for the H2SO4, like that you can try for the Cl2O7. I told you SO3, okay? So one fine day you can, if you are not, if your Wi-Fi is not working and your cable TV not working, then you can go for this as a time pass, okay? So, but as per modern concept, daily, okay? Dative bond structure of all these. Structure of all these example must be shown with double bonds. Okay. So these are some exceptions and I have written here. So, but you can try yourself, then we will go for it. Okay. So I think coordinate covalent bond, it is clear now. Now let's study some properties, then we will. Okay, next, properties of coordinate covalent bond. The compounds containing coordinate covalent bonds show the melting and boiling points higher than those of pure covalent bond. Okay, if they contain only covalent bond, their melting and boiling points are less. But if they contain more covalent bonds, then what they will have? Higher covalent melting and boiling point. And they are soluble in organic solvent, sparingly soluble in water. They act as a single bond directed in specific orientation. Hence, they will show the isomerism also. That is stereoisomerism that you will come to know especially in the organic. Okay. Like covalent compounds, they are also poor conductors. These are the some important properties of the coordinate compounds. Okay. Okay, after completion of coordinate covalent bond, now next topic is molecular orbital theory. Okay, here it was proposed by Hunt and Mulliken. It is proposed by Hunt and Mulliken. Okay, to explain paramagnetic nature, the main reason, like it was for ammonia to explain the Arrhenius unable to explain the basic character of ammonia. Okay, so because of that, that entire theory failed. And hybridization was excellent concept. Valency bond theory was excellent concept. VSEPR theory was excellent concept. Only the problem came is with they are unable to explain paramagnetic nature of oxygen molecule. Okay, so sometimes very big things will stop just because of small mistakes. Okay, so this is a live example that all the three theories failed. What are the theories? VSEPR theory, valency bond theory, and hybridization. All theories failed just because they are not able to explain the paramagnetic nature of oxygen molecule. Arrhenius theory was excellent. Everything it was able to explain. But one molecule made it life miserable. Okay. Who is that? Ammonia molecule. So like that, to explain the paramagnetic nature of a molecule, electrons in a molecules are present in various molecular orbitals as the electrons of an atom present in the various atomic orbitals. Okay. So here in the previous topic in the hybridization, we studied atomic orbitals of the same atom combined together to give the hybrid orbital. Here what we will say, atomic orbital of the both atoms. Okay. So there suppose P is combining with Cl, then hybridization is done only atomic orbital of phosphorus only. But here in case of the microorbital theory, it says that both will provide their atomic orbital for LCAO. The process there it is called as a hybridization. There it is called as what? Hybridization. Atomic orbital undergoes hybridization. Okay, undergoes hybridization to give the hybrid orbital. But in this topic, what we will do, the differences are simple differences. All the atomic orbital belonging to one atom undergo hybridization to give hybrid orbital. Here the difference is atomic orbital of both atoms will undergo LCAO. What is LCAO? That I will tell you. To give molecular orbital. There they are giving hybrid orbital. Here they will give you the molecular orbital. Okay. So what is common in them? Only common is atomic orbital. Okay. So LCAO stands for linear. Okay. L stands for linear. C stands for combination. And O stands for of atomic orbital. LCAO. Sorry. A stands for atomic. O stands for orbital. Okay. So LCAO, that is like just like a hybridization only, but a new word is introduced, and both atomic orbital will be of the similar energy but differing the atoms. They will be from the both different atoms. Okay, so they will not belonging to the same atoms. So let's see the next one. Okay, LCAO. This is what I told you, linear combination of atomic orbital of comparable energies. There also same 2s mixed with the 2p. Okay, and proper symmetry. So this means that 1s orbital can combine with 1s orbital, but not with 2s orbital, comparable energy. Okay. So this is true only for homonuclear diatomic molecule. So first condition is it should be applicable for only two atoms. Okay. And homonuclear is more, and it is nowadays it is extended for heteronuclear also. Earlier it was considered as applicable for only N2, O2, F2, like this only. These are called as a homonuclear diatomic molecule. And here for overlapping, they have taken Z axis as a molecular axis. Okay. So therefore 2pZ can combine with 2pZ for the sigma bond. But 2px cannot combine with 2py of the other atoms because they will lie perpendicular to each other. Molecular orbital is polycentric. Okay, that means both. Here in hybrid orbital, suppose phosphorus is there. So only phosphorus is responsible for that, monocentric. But here it will be polycentric. Suppose nitrogen is forming, one center will be nitrogen, another center will be another nitrogen. Okay, so that's why it is called as a polycentric. Okay, you can make your own notes. Left side write down molecular orbital theory, right side you can write as a hybridization. Okay, then it will be easy to understand and minimizes your confusion. Main problem is confusion. Okay, so that confusion will be out if you go through this method. Okay, so let's see the next one. Okay, next one is number of molecular orbital formed equal to number of combined atoms. This was same there also. Number of hybrid orbitals. Suppose 1s and 3p combines, 4sp3 orbital will be there. Same way, number of molecular orbital is equal to number of combined atom. Two atom combines, two molecular orbital will be formed. When two atomic orbital combine, two molecular orbital will be formed. But one of them is known as bonding molecular orbital, another is called as a anti-bonding molecular orbital. Okay. Suppose atomic orbital plus atomic orbital, when they undergo molecule, what do you call LCAO? Okay, when they undergo LCAO, two molecular orbital will be there. One molecular orbital is called as a BMO, bonding molecular orbital. Another molecular orbital is called as a ABMO, anti-bonding molecular orbital. Okay, it may be noted that bonding molecular orbital is stabilized because of the BMO. Stability increases, energy decreases. Okay, BMO, what happens? It will increase the stability. Stability, it improves. More bonding orbital, more will be the stability. Why stability is high? Because energy is low. What is low? Energy will be low. Understood? Then just opposite to it, anti-bonding molecular orbital destabilizes the molecule. Destabilizes the molecule because they have the higher energy. Okay, but total energy will be equal to atomic orbital. Only thing, redistribution will be there. Let us take, I will write it in the other color. Okay, let us take this have a 10 kilojoules, this have the 10 kilojoules. Both total will have 20 kilojoules, but this will have 5 kilojoules, this will have as a 15 kilojoules. So redistribution is taking place. As it is having less energy, more stable. As it is having more energy, less stable. That is called as a molecular orbital theory. Number of hybrid orbital, number of molecular orbital formed is equal to number of atomic orbital combined. Okay, then order of energies of various orbital bonding, orbital non-bonding less than anti-bonding. Okay, so without molecular orbital theory, without LCAO, whatever they are there, they are called as a non-bonding orbital. If they participate in LCAO and forms the bonding microorbital, their energy will be less. If they form anti-bonding, then energy will be more. Okay. So like this, I will write here it is atomic orbital. Atomic orbital. Okay. Above it will be anti-bonding molecular orbital. Below will be bonding molecular orbital. So energy wise, when you go like this, first you will get the bonding molecular orbital, then you will get the atomic orbital or what do you call non-bonding orbital, and the anti-bonding is already there. Okay, this is the energy level diagram. This is which diagram? Energy level diagram. Very important. Then electrons are filled as per the Avro principle. Avro principle, what does it says? Fill the electrons in the lower energy level. So once I have to fill the lower energy level, which will get the first electron? Okay, according to our principle, any orbital having less energy must be given electron. So bonding molecular orbital will get the electron, then we will go for the anti-bonding. That is first one. Second, Pauli's exclusion principle says that any orbital, atomic orbital, hybrid orbital, molecular orbital, f orbital, d orbital, p orbital, Pauli says that you will can fill up maximum how many electrons? How many electrons you can fill irrespective of type of orbital? You can fill only two electrons. Therefore, any molecular orbital get two electrons. Hunt says that suppose two orbitals are like this, then you will fill the electron like this, then you will pair up. So this small sentences, small word have a lot of meaning. Okay. Then microorbitals are named as a sigma pi. Okay, and at the microorbitals are formed by LCAO method. Okay, according to the wave mechanics, atomic orbital expressed by the psi. Okay, which represent amplitude of the wave. So this is representation is very important. How it is represented, that we will come to know now. Okay. Okay, atomic orbital of two hydrogen atoms. Suppose there are how many hydrogen atom? Two hydrogen atom. Okay. So LCAO means it can be plus, it can be minus. That is only LCAO, nothing new. What is psi? Psi is a atomic orbital representation. And when you combine both of them, molecular orbital will be formed. So here if I take plus, that means bonding orbital. If I take minus, anti-bonding orbital. Okay. Quantitatively, additive combination. Which combination? Additive combination of molecular orbital give bonding molecular orbital, and subtractive minus you are using, therefore it will give as a subtractive molecular orbital. Okay. So formation is a destructive interference. Subtractive is also called as a destructive, and one molecular orbital is constructive. Plus means constructive, minus means subtractive or destructive. Okay. So this is about the representation of molecular orbital. Okay. Now let's see the next part. So during the ABMO formation, electron waves cancel out each other due to destructive. So crest will combine with the trough, then there is no value. Okay, the electron density in the bonding molecular orbital located between the nuclei, whereas electron density in the antibonding molecular orbital located away from the space. Okay, so I will draw it here. Suppose this is A, this is B. In anti-bonding, the location will be like this. Location will be like this. So you will find a plane over here which is not having any electron density. So that plane is called as a nodal plane. But in case of the bonding molecular orbital, and both will be like this, there is no nodal plane. Electron density is maximum in the center. Okay. So located between the nuclei where it is bonding. Okay, this is the bonding and this is anti-bonding. Okay, so if A is here, B is here, this side if electron density is there, then anti-bonding. If it lies between them, it is called as a bonding molecular orbital. Electron density and nodal planes. This is about the electron density and nodal planes. So how to write electronic configuration? Okay, first of all you have to add total electrons. If you get 14 electrons are less than, okay, so 14 are less than, then you will write like this: sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than pi 2px equal to. So whenever there is a equal, you will write first 1 electron. Then if you get electron, you will write the second electron. Okay. Then if you get, then you will write the third electron, fourth electron, likewise. But in this one, there is no problem. You will give electrons sufficient for the 2s, sigma 2s. Then you will give the electron for the star sigma 2s. And this you will follow when 14 electrons or less is there. If more than 14 electrons are there, then this is a new rule. Okay. So now carefully observe and tell me what is the change between this one and this one. Let me check your observation power. Okay, here, see here. In this, you will find pi orbital are coming first. Okay, but here sigma is coming first, and here sigma is coming afterwards. Pi is coming uh, afterwards here. Okay, that is the difference. Above 14 like this, below 14 like this. You try any times, but there are chances when you go to the exam, then there will be confusion. Above 5 it was like that, or below 5, 14 like that. Okay, simple. All students are, all human beings are very constructive up to their age 14. Okay, once their age is above 14, all tinkering and all wrong habits will start. They will become ulta triangle. Okay, up to 14 they are see the triangle, and once they cross the age of 14, then they will start doing all nonsense things. Okay, so this is what you will remember. Now you will ask how it is related to that. See, pi 2px equal to pi 2py. This is pi 2px equal to pi 2py. Okay, and this will be sigma 2pz. After that it will be sigma 2pz. But once you are above the 14 electrons, okay, once electrons are crossed above, then ulta triangle. Ulta triangle means first what it will be, otherwise I will draw it afterwards. Okay, this is below 14. Okay, this is where below 14. This is below 14. Okay, once he crosses above 14. Okay, above 14 I will write it here. So above 14, then the person will become ulta. Okay, all doing ulta things. Okay, so like this. That means you will fill the sigma first. 1 means sigma. Okay, sigma 2pz, and 2 are at the parallel. Then it will be pi 2px is equal to pi 2py. Now there is no confusion. Okay. So here first to pi, then sigma up to 14, and after 14 first sigma, then pi orbital. Okay, so this is the electronic configuration, and it is orbital, therefore everywhere you will start filling up. Suppose Be2. Okay, so Be2, what will be the electrons? Total electron 2 into beryllium. So 2 into what is the atomic number? 4. So it will be 8. 8 electrons are there. Then you will be using this one. Okay. So I will clear this. Then I will write now. Okay. So 8 electrons I have. Sigma 1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2. So this is the electronic configuration of what? Be2. Okay. Suppose question is about the C2 minus. So then what you will write? 2 into carbon plus 1 electron. Minus 1 means electron is added. So 2 into 6 plus 1, 12 plus 1, 13. So 13 electron I will fill. So before, below 6, 14, this one. So I have added up to 8. 8, 9, 10, 11. Again I will fill up like this here. 11, 12, 13. So this is the configuration of C2 minus. Okay. Suppose C2 2 minus, one more electron. So one more electron you will add like this. Suppose question is about the 8, 14 also. N2 also the same, C2 2 minus only. Okay. That also I have written. You will get it in the next slide, I hope. So this is how you will write the electronic configuration of molecules, ions, everything you can write down by using just simple trick. Okay. Now this is the diagrammatic representation. Okay. So here additive combination means bonding. Okay. So in the additive combination, what I told you, electron density will be maximum between the orbital. See, electrons are maximum here. Okay. Between the nucleus. But subtractive anti-bonding. See, this is the center. This side electrons are there. This side. So this is what the nodal plane. What plane? Nodal plane is there. Okay. Next, this is about the S and S. Okay. And already I told you p orbital can form sigma bonds and pi bond, but s orbital cannot form pi bond. So we cannot discuss here pi bond. And here p orbitals addition. So addition means here plus. See, all are both are added here. Okay. Actually, this size will be bigger than these two. Understood? Subtraction minus. So they will be just separate here. Okay. And pi bond. These are the both are sigma bonds. Okay. Now this is about the pi bond. In the pi bond, see pi plus with plus. So this will be above the line. Here also nodal plane will be there. Nodal plane, that is bonding. And subtraction again nodal plane like this. Okay. So these diagrams useful in the board exams, and in competition they may ask about the nodal plane. Okay. So that is the difference. Then bond order, very important topic I promised you during the bond parameter. I told you I will tell you will come to know when we discuss. Okay. So bond order is simply formula. See here. Number of bonding electron minus number of anti-bonding. Okay. So like in the previous sheet, we will write the electronic configuration. Okay. So this, sorry, not this one, before this one. So suppose here, example I am taking here. Two electrons are here, two electrons are here, two electrons are here, two electrons are here. One electron is here. So number of bonding electrons. So this is not having star, so bonding. Not having star, bonding. It is having star, non-bonding. So it is bonding and bonding. So total bonding electrons are 2 plus 2 plus 2, 6. And Na, anti-bonding. So anti-bonding star star, only two are there. Okay. Therefore 4. Is it understood? Like that 6 minus 4 will be Nb minus Na by 2. So then answer will be 2 by 2, that is 1 bond. Bond order is equal to how much? 1. Like this you have to find out the bond order. Okay. So let's see the bond order formula once again, so that you can get idea. Half into Nb minus Na. Very simple. Mark out the star one. Whichever is having the star, that is anti-bonding. Without star, electrons are bonding. Bonding minus anti-bonding by 2, you will get the bond order. So there already I have discussed. Again, I will explain here also. Higher the bond order means number of bonds are more. So bond energy will be more. So more bond energy means more stable is the molecule. Okay. So bond order can be utilized to compare the stability, compare the bond energy, compare the bond length also. Okay. Because more bonds means bond length will be less. Okay. This is what the bond order topic. Now let's see the next one. Next topic is hydrogen bond. Okay. So hydrogen bond is a weak electrostatic force of attraction. Hydrogen bond is what? Weak electrostatic force of attraction between positively charged hydrogen. See, name itself is about the hydrogen. So there is no chance other element will come. Positive element will be what? Hydrogen. But negative element can be anybody. Highly electronegative atom in the world. There are only 3 people are highly electronegative in the world. What are those? Phone. This is also memory technique. Okay. So in our lecture only will get so many memory techniques which will make you chemistry easy, and top secrets also revealed. Okay. So you will remember phone. If somebody asks what are the electronegative elements, say phone, sir. Phone means fluorine, oxygen, nitrogen. Okay. So these three elements, when they form bond with hydrogen, okay, that too apart from the own, okay, it should be extra. Is it understood? So when something extra with hydrogen, then it is called as a hydrogen bond. Now highly electronegative may be present in the same molecule or in the different molecule. Okay, it can be from the different molecule also. It can be from the different molecule also. If it is from the same molecule, it is called as a intra. If it is between the two different molecules, then it is called as a inter. What is that? I am telling you here itself because I don't want to take risk. Suppose here this is one water molecule, okay, and this is another molecule. This is a hydrogen of this molecule, this is hydrogen of this molecule. And there will be hydrogen bond. Hydrogen bond is denoted by dot dot dot. Okay. So it is between the two molecule. Therefore, it is called as a inter. Whenever you say inter means between, not I am talking about the intermediate. Inter means is like international match, two nations match, inter-school competition, between two schools competition. Okay, interstate bus terminal. In Delhi, there is a called as a ISBT. ISBT means interstate bus terminal. So between two states, whatever the buses are moving, they will stop there. Okay. So inter means between. So between two hydrogen bond, between two molecules are there. Therefore, it is called as a intermolecular hydrogen bonding. Sometimes the molecules are very huge, so they need not to do anything. That time it will be intramolecular. Let us take this is a benzene. Here it is OH and here it is COOH. Okay. So within the molecule only hydrogen bond is possible. Then that is called as a intra. That is called as what? Intra. Okay. Suppose in your school only competition is there. Then you will say intra school competition. Okay. So within the school, intra school. Okay. Inter school, between the two schools. So length of the hydrogen bond depends on the substance under investigation. Don't worry, investigation is not that CBCID. Okay. So this is what we are studying. So 1.79 angstrom to 2.75 angstrom. Okay. Then hydrogen energy also varies from 2 to 10 kilocalories and 10 to 50 kilojoule per mole. Okay. If you can remember, it is good. Not remembering also chalega. Okay. Now let's see the next sheet about the hydrogen bond. What it says. Hydrogen bond is okay. Hydrogen bond is weaker than the covalent bond. Okay, and stronger than the van der Waals force of attraction. Okay, most electronegative elements like fluorine, oxygen, nitrogen only can involve in hydrogen bond. Question will be reasoning question. Why chlorine does not form hydrogen bond? Rarely, because of its large atomic size. What will be the answer? Due to large atomic size. Okay. Then hydrogen bond present in the same molecule. Already I told you intramolecular. Okay. So due to intramolecular hydrogen bonding, ring formation will takes place. Simple. This is already benzene is there, and there will be one more ring like this. There will be hydrogen bond like this. Okay. So examples are orthochlorophenol. Orthonitrophenol is more important example. Orthonitro. Ortho, why they are saying like this? Because they should be nearby. Then only this hydrogen bonding can exist. It is not that one is OH is here and NO2 is here. Then they cannot form the hydrogen bond. Which one? Intramolecular. And it is not that they will not undergo hydrogen bond. They will undergo hydrogen bond with another molecule. That time inter. Para will be inter, ortho will be intra, and meta will be nothing. Okay. So ortho-hydroxybenzaldehyde, ortho-hydroxybenzoic acid, these are called as a salicylic aldehyde, salicylic acid. Okay. Then the substances having intramolecular hydrogen bond are less water soluble and steam volatile. So this is the consequences of hydrogen bonding. Okay. If they are forming intra, then why they wanted to mix with water molecule? When everything they are getting within the home itself, why they will go for outside? Okay. Suppose you are getting all pictures in your home only, that too in home theater. Why you will go outside to the picture hall? Same problem with the intra. So already they are having hydrogen bond within the molecule. Why they will dissolve in water? Okay. And why they wanted to go outside? So they will go outside only when complete requirement is there. Steam, when you force it to go out. Okay. And they have low boiling point. So they don't speak to anybody. They are within the one molecule. Therefore, easily boils. Hydrogen bond formed between the different is called as a intermolecular, and its properties will be just opposite. Okay. See, effect of hydrogen bond. Very, very important topic. This is the interlinking of two chapters. So because of hydrogen bond, already I told you, interhydrogen bonding will increase boiling point. If it is intermolecular, which molecular? Intermolecular. See here, there is no problem here. Down the group, here carbon, silicon, germanium, tin. So these are the hydrates. So down the group size increases, therefore boiling point decreases. So lowest boiling point is CH4. Okay, there is no problem. But problem will start here. See, ammonia is supposed to be where according to this? It is supposed to be here. Okay, because NH3, PH3, ASH3, like this SbH3. But why it jumped here? Because of the hydrogen bonding. Why instead of lowest it is second highest? Just because of the hydrogen bonding. See, water is very, very important. Here it should be lowest but exceptionally highest. HF should be lowest, exceptionally highest. These are the consequences of hydrogen bonding. Due to hydrogen bonding, their boiling point will increase. Okay. So that is very important question, and so many times it is asked, and this time also they may ask. KHF2 exists but not KHCl2 because of the hydrogen bonding. Okay, wherever you will get, this is also top secret. Suppose in your exam there is option like hydrogen bonding, blindly tick that. Okay, all these anomalies will be hydrogen bonding only. This is an integer type question. HF can exist as a hexamolecular. 6 molecules can combine together because of the hydrogen bond. Okay. Then only H2O molecule in vapor state can have HF. Okay. And molecular weight of formic acid. This is also very important. Doubles. See, they are combining together just because hydrogen bonding. Dotted line is hydrogen bonding. This is called as a dimerization. What it is called as? This is called as a dimerization. Okay. Because of dimerization, they will combine with each other. Okay. Now, ice very, very, very important. Why ice floats over the water? Okay, because in ice, water molecule involves 4 hydrogen bonds. Integer type question. Each water molecule contains 4 hydrogen bonds and tetrahedral. Okay, so this I will try to draw here. This is one water molecule, second water molecule, third water molecule, fourth water molecule. Okay, so this is the central, and this is one H2O. Okay, and this is another H2O. Okay, this is another H2O. Again I will draw. Okay, here what is the meaning of that 4 hydrogen bonds I am showing you here. So this is a tetrahedral also. What is this tetrahedral? See, when I join these water molecule, these are the 4 water molecule. Okay, So 4 water molecule when I join them. Oh shit. Okay, when I join them, then I will get a regular tetrahedron. Okay, this is a regular tetrahedron. At the center, you will find out one more water molecule. Okay, so here each oxygen is attached to two hydrogen. Okay, now this will also will have hydrogen bond. See, this each oxygen is connected to total 4 hydrogens. See, this is one hydrogen bond, this is another hydrogen bond. Okay. Same way here, this will be forming hydrogen bond with one oxygen. So as a total, if you take one molecule, you will find 4 hydrogen bonds. Two hydrogen bonds are with, okay. So two hydrogen bonds are with two oxygen with two hydrogen bonds with hydrogen with two oxygens. Okay, so let us take this as separately now easy. So this will form two hydrogen bond. This will form one hydrogen. This will form one hydrogen. So total there will be 4 hydrogen bonds. Okay, so because of this, this is called as a cage-like structure. What it is called as cage-like structure. So in the cage-like structure, there will be lot of empty space. So because of this empty space, volume will be more. So density will be less. That's why ice floats over water. Okay. This reason and like this wonderful diagram, if you draw, you will get full out of full. Numerator will be equal to denominator. Then, and one more in the medical and in the biomolecules of class 12 second year, you will get two DNA molecule strands are joined by hydrogen bond. So in the DNA there will be, you must have seen like this. One will ribbon like comes like this, another will come like this. So between them there will be hydrogen bond. Okay. Then covalent substances like glucose, urea, sugar, ammonia, ethyl alcohol all dissolve freely in water because of the hydrogen bond. Hydrogen bond improves the solubility. That is also one of the advantage of hydrogen bond. Okay. 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 Is it understood now? Okay. Now let's see the next one. So covalent substances, this is already explained. So 1 or 2 points only there. Intermolecular hydrogen bond. They have high boiling point and they are not steam volatile. Just whatever the intra is there, just opposite to that. They were steam volatile. These are not steam volatile. They are not water soluble. These are water soluble. Hydrated cation and bond between the water is called as a dative bond. Okay. So in the suppose Cu2 plus. So if we write as a H2O4, okay. So and one more H2O will be there out of that. That will be fifth H2O. Total 5 H2O are there. So that will be the hydrogen bonded. Okay. Same way even number, odd number. These are the some examples. Dot 4 H2O it can be. Dot single H2O also it can be. Okay. So examples are written here. 7H2O, 4H2O, 6H2O, just you can go through them. Okay. So these are the even number example. Most hydrogen bonds are asymmetric. That is not located exactly between the both because one may be more electronegative, another. This is strong bond. Covalent bond is strong bond, so it will be very nearby. And this is weak bond, therefore it will be away. So valence angle between VIJ bond varies between 100 to 140. Okay. So that's all. This is about the chemical bonding, and I hope all of you understood everything. If you got any problems, still you can ask.